Tonight, we journey through the complete story of asteroids and comets, from their ancient birth in swirling cosmic clouds to the spacecraft we have sent to touch their surfaces. To truly understand asteroids and comets, we must travel back in time approximately 4.5 billion years, to an era before Earth existed, before the sun had ignited, before any of the planets had formed. We must journey to a time when our entire solar system was nothing more than a vast cloud of gas and dust drifting through the galaxy. This cloud, called the solar nebula, contained all the raw materials that would eventually become everything we know. Every planet, every moon, every asteroid and comet, and even the atoms that make up your own body. Let us settle into this primordial scene and watch as the cosmos slowly assembles itself into the solar system we call home. The solar nebula was not unique. Throughout our galaxy, similar clouds of gas and dust exist today, and astronomers can observe them in various stages of collapse and star formation. These clouds are composed primarily of hydrogen and helium, the simplest and most abundant elements in the universe, created in the first moments after the Big Bang. But mixed into this primordial gas are heavier elements forged in the cores of earlier generations of stars and scattered into space when those stars exploded as supernova. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements were present in the solar nebula, though in much smaller quantities than hydrogen and helium. These heavier elements would prove crucial to the formation of rocky bodies like asteroids and the icy bodies we call comets. Something disturbed the solar nebula approximately 4.6 billion years ago. Perhaps the shock wave from a nearby supernova explosion, perhaps the gravitational influence of a passing star, or perhaps simply the random turbulence that exists within all such clouds. Whatever the cause, regions of the nebula began to collapse under their own gravity, drawing material inward and growing denser with each passing moment. As the cloud contracted, it began to spin faster, just as a figure skater spins faster when pulling their arms close to their body. This rotation flattened the collapsing cloud into a disc shape, with most of the mass concentrated in the centre where the proto-sun was forming. The centre of this disc grew increasingly hot and dense as more material fell inward. Eventually, the temperature and pressure at the core became so extreme that hydrogen atoms began fusing into helium, releasing enormous amounts of energy. The sun had ignited, flooding the surrounding disk with light and heat. But around this newborn star, the disk of gas and dust remained, and within this disk, the process of planet formation was just beginning. The temperature within the disk varied dramatically with distance from the young sun. Close to the star, temperatures were so high that only the most refractory materials, those with the highest melting points, could exist as solids. Metals and rocky silicates could survive in this region, but water, ammonia, methane, and other volatile compounds remained as gases. Farther from the sun, beyond a boundary that astronomers call the frost line or snow line, temperatures dropped low enough for water ice to form. Beyond this line, ice became a major building block for forming bodies, dramatically increasing the amount of solid material available. The process of building larger bodies from this disk of gas and dust began with the gentle collision and sticking of tiny particles. Microscopic grains of dust, each smaller than a grain of sand, drifted through the disk and occasionally bumped into one another. Some of these collisions caused the grains to stick together, held by electrostatic forces or simply by the irregular shapes of the particles interlocking. Over thousands of years, these tiny aggregates grew into pebbles, then into rocks, then into boulders. This process, called accretion, was slow and gradual, but time was abundant in the early solar system. As these growing bodies reached sizes of 1 kilometre or more, their own gravity began to play a role, attracting additional material and accelerating their growth. These kilometre-sized objects, called planetesimals, were the building blocks from which planets would eventually form. In the inner solar system, planetesimals were composed primarily of rock and metal, the only materials that could remain solid in the intense heat near the young sun. In the outer solar system, beyond the frost line, planetesimals incorporated vast quantities of ice along with rock and metal, making them fundamentally different in composition from their inner solar system cousins. The asteroids we observe today are the survivors and remnants of this planetesimal population from the inner solar system. They represent material that never successfully assembled into a planet, frozen in time at an early stage of the planet-building process. The region between Mars and Jupiter, where most asteroids now reside, was particularly affected by the gravitational influence of Jupiter, the largest planet in our solar system. Jupiter formed quickly, within perhaps the first few million years of the solar system's history, and its immense gravity stirred up the orbits of planetesimals in the adjacent region. Instead of gently accreting into a planet, these planetesimals collided with each other at high velocities, shattering rather than sticking together. Jupiter's gravity also ejected many planetesimals from this region entirely, scattering them into the outer solar system or flinging them out of the solar system altogether. The total mass of the asteroid belt today is remarkably small, only about 4% of the mass of Earth's moon. This meagre amount represents just a tiny fraction of the material that originally existed in this region of the solar nebula. Most of the primordial mass was either ejected by Jupiter's gravity or swept up by the growing planets during the chaotic early history of the solar system. The asteroids that remain are precious survivors, samples of the original building blocks from which the terrestrial planets formed, preserved in the cold vacuum of space for 4.5 billion years. Comets have a different origin story, though they formed from the same solar nebula during the same epoch. The icy planetesimals that became comets formed in the outer solar system, beyond the frost line, where temperatures were cold enough for water and other volatile compounds to freeze solid. These icy bodies incorporated not only water ice, but also frozen carbon dioxide, carbon monoxide, methane, ammonia, and a complex mixture of organic compounds. The composition of comets reflects the composition of the cold outer regions of the solar nebula, preserved in frozen form across the vast span of cosmic time. Many of these icy planetesimals were incorporated into the cores of the giant planets, Jupiter, Saturn, Uranus, and Neptune. These planets grew large enough to capture enormous atmospheres of hydrogen and helium, becoming the gas and ice giants we observe today. But countless other icy planetesimals were not captured by the giant planets. Instead, gravitational interactions with the growing giants scattered these small bodies outward into the distant reaches of the solar system, far from the warmth of the sun. The Dutch astronomer Jan Oort proposed in 1950 that a vast spherical shell of icy bodies surrounds the solar system at distances of tens of thousands of astronomical units from the sun. This region, now called the Oort Cloud, is thought to contain billions or even trillions of icy bodies, the scattered remnants of the planetesimal population that formed in the giant planet region. These distant objects orbit so far from the sun that they are barely bound to our star at all, and occasional gravitational perturbations from passing stars or the galactic tide can nudge some of them onto orbits that bring them into the inner solar system. When one of these icy wanderers approaches the sun, solar heating vaporizes its frozen gases, creating the spectacular tail that defines a comet. Closer to the sun, but still in the outer solar system, lies another reservoir of icy bodies called the Kuiper Belt. This donut-shaped region extends from the orbit of Neptune outward to perhaps 50 or 60 astronomical units from the Sun. Unlike the Oort Cloud, which formed from objects scattered outward by the giant planets, the Kuiper Belt contains objects that formed more or less in place in the cold outer reaches of the original solar nebula. Pluto, once considered the ninth planet, is now recognized as one of the largest members of the Kuiper Belt population. The Kuiper Belt supplies many of the short-period comets that visit the inner solar system, objects whose orbits bring them close to the Sun on timescales of decades rather than millennia. The formation of the solar system was not a smooth, orderly process, but rather a chaotic, violent epoch lasting hundreds of millions of years. The giant planets likely did not form in their current positions, but migrated through the solar system as they interacted with the disk of gas and planetesimals. One influential model, called the Nice model, after the French city where it was developed, proposes that the giant planets formed in a more compact configuration and later migrated outward, with Neptune moving from inside the current orbit of Uranus to its present position at the outer edge of the planetary system. This migration would have scattered the Kuiper Belt, ejecting many objects into the Oort Cloud or out of the solar system entirely, while trapping others in resonant orbits with Neptune. The migration of the giant planets also triggered a cataclysmic event called the Late Heavy Bombardment, a period approximately 4 billion years ago when the inner solar system was pummeled by a surge of impacts from asteroids and comets. The gravitational reshuffling caused by planetary migration destabilized populations of small bodies that had previously been in stable orbits, sending them careening through the solar system. The scarred face of the Moon preserves a record of this bombardment, its ancient highlands saturated with impact craters dating to this violent epoch. Earth, Venus, Mars and Mercury all experience similar bombardment, though geological processes have erased most of the evidence on Earth. This bombardment may have played a crucial role in delivering water and organic compounds to the early Earth. Although Earth formed inside the frost line, where water could not condense from the solar nebula, impacts from water-rich asteroids and comets could have supplied the oceans that now cover most of our planet's surface. Some researchers estimate that a significant fraction of Earth's water arrived via these cosmic deliveries, making asteroids and comets essential contributors to the habitability of our world. The organic compounds found in comets and certain types of asteroids may have similarly contributed to the chemical building blocks from which life eventually emerged. As we rest here contemplating the birth of our solar system, we can appreciate that asteroids and comets are not merely debris or leftovers. They are time capsules, preserved samples of the original material from which our entire planetary system formed. When we study asteroids and comets, we are studying our own origins, examining the building blocks that came together to create Earth and everything upon it. The atoms in your body were once part of the solar nebula, perhaps incorporated into a planetesimal that was later shattered in a collision, its fragments eventually swept up by the growing Earth. In a very real sense, we are all made of asteroid and comet stuff, children of the same cosmic cloud that gave birth to these ancient wanderers. Between the orbits of Mars and Jupiter lies a region of space that has captured human imagination ever since its existence was first suspected. The asteroid belt, home to millions of rocky bodies ranging from tiny pebbles to dwarf planets hundreds of kilometers across, represents one of the most fascinating and misunderstood features of our solar system. Let us drift gently into this realm of ancient stone and discover what really lies within this celestial archipelago. The discovery of the asteroid belt began with a mathematical curiosity. In the late 18th century, astronomers noticed an intriguing pattern in the spacing of the known planets. A numerical relationship called the Titius-Bode law seem to predict the distances of planets from the Sun with surprising accuracy. Mercury, Venus, Earth, Mars, Jupiter, and Saturn all fit the pattern reasonably well. But the law also predicted that a planet should exist in the gap between Mars and Jupiter, a region where no planet had ever been observed. This mathematical hint inspired a group of astronomers to organise a systematic search for the missing planet. On the first night of the 19th century, January 1st, 1801, the Italian astronomer Giuseppe Piazzi discovered a new object while working on a star catalogue at the Palermo Observatory in Sicily. The object moved against the background stars, indicating it was a member of our solar system rather than a distant star. Piazzi initially thought he had found a comet, but the object's motion suggested a nearly circular orbit in precisely the region where the Titius-Bode law predicted a planet should exist. He named the object Ceres after the Roman goddess of agriculture and the patron deity of Sicily. Ceres proved to be much smaller than expected for a planet, with a diameter of only about 940 kilometres. For comparison, Earth's moon has a diameter of about 3,474 kilometres, making Ceres less than a third the size of our lunar companion. Nevertheless, Ceres was celebrated as the missing planet predicted by the Titius-Bode law, and Piazzi was honoured for his discovery. But the story did not end there. Within a few years, astronomers discovered additional objects orbiting in the same region of space. Heinrich Olbers discovered Pallas in 1802 with a diameter of about 512 kilometres. Carl Harding found Juno in 1804, measuring roughly 250 kilometres across. Olbers discovered Vesta in 1807, a body about 525 kilometres in diameter. Suddenly, instead of one missing planet, astronomers had found 4 small bodies sharing the same orbital neighbourhood. William Herschel, the discoverer of Uranus, proposed calling these objects asteroids, meaning star-like, because they appeared as points of light rather than showing visible disks like the larger planets. The discovery of additional asteroids continued throughout the 19th century, with the pace accelerating as photographic techniques made detection easier. By 1900, astronomers had catalogued over 400 asteroids. By 1950, the count had risen to several thousand. Today, we have identified and tracked more than 1 million asteroids, with millions more remaining to be discovered. The asteroid belt is far more populous than early astronomers imagined, though as we shall see, it is also far emptier than popular culture often suggests. One of the most persistent misconceptions about the asteroid belt concerns its density. Science fiction films often depict spacecraft navigating through dense fields of tumbling boulders, dodging collisions at every turn. In reality, the asteroid belt is overwhelmingly empty space. If you were to fly a spacecraft through the asteroid belt, you would be extraordinarily unlikely to encounter any asteroid unless you specifically aimed for one. The average distance between asteroids larger than 1 kilometre is approximately 1 million kilometres, several times the distance from Earth to the Moon. Spacecraft travelling to the outer planets routinely pass through the asteroid belt without any special manoeuvring to avoid collisions. This emptiness reflects the small total mass of the asteroid belt. Despite containing millions of individual objects, the combined mass of all asteroids is only about 4% of the Moon's mass, or roughly 0.05% of Earth's mass. If you gathered every asteroid into a single body, it would be smaller than Earth's moon. The largest single object, Ceres, contains about 1/3 of the total mass of the asteroid belt. Add in the next 3 largest asteroids, Vesta, Pallas and Hygeia, and you have accounted for more than half the belt's total mass. The remaining millions of asteroids share the other half, with most being tiny fragments measuring metres or less across. Ceres holds a special status among asteroids. In 2006, the International Astronomical Union created a new category called dwarf planets, defined as bodies massive enough for their own gravity to pull them into roughly spherical shapes, but not massive enough to have cleared their orbital neighbourhoods of other debris. Ceres met the criteria for dwarf planet status, making it the only dwarf planet in the inner solar system. Pluto, Eris, Makemake, and Haumea are the other recognised dwarf planets, all located in the distant Kuiper Belt. The composition of asteroids varies considerably, depending on their location within the belt and their individual histories. Astronomers classify asteroids into several broad categories based on their spectral properties, the way they reflect light at different wavelengths. The three main categories are C-type, S-type, and M-type asteroids, though many additional subtypes exist. C-type asteroids, where the C stands for carbonaceous, are the most common type in the outer regions of the asteroid belt. These dark, carbon-rich bodies reflect only 3 to 4% of the sunlight that falls on them, making them among the darkest objects in the solar system. C-type asteroids are thought to be relatively primitive, meaning their composition has changed little since they formed in the early solar system. They contain significant amounts of water bound within hydrated minerals, as well as organic compounds, including amino acids, the building blocks of proteins. The asteroid Bennu, visited by NASA's OSIRIS-REx mission, is a C-type asteroid, and samples returned from Bennu have confirmed the presence of water and organic molecules. S-type asteroids, where S stands for silicaceous or stony, dominate the inner regions of the asteroid belt. These bodies are composed primarily of silicate minerals like olivine and pyroxene, along with metallic iron and nickel. S-type asteroids are brighter than C-types, reflecting 15 to 25% of incident sunlight. They are thought to represent material that was heated more intensely during the early solar system, driving off volatile compounds and leaving behind rocky residue. The asteroid Itokawa, visited by Japan's Hayabusa mission, is an S-type asteroid. M-type asteroids, where M stands for metallic, are composed primarily of iron and nickel, the same metals that make up Earth's core. These asteroids may be the exposed cores of larger bodies that were once differentiated, meaning they were hot enough for heavy metals to sink to the centre, while lighter rocky material floated to the surface. Subsequent collisions shattered these differentiated bodies, exposing their metallic cores. The asteroid Psyche, target of an upcoming NASA mission, is the largest known M-type asteroid, measuring about 226 kilometers in diameter. If Psyche is indeed a remnant planetary core, it offers a unique opportunity to study materials that are normally buried thousands of kilometers beneath a planet's surface. The asteroid belt is not uniformly distributed, but shows distinct structure shaped by the gravitational influence of Jupiter. Certain orbital distances are notably depleted of asteroids, regions called Kirkwood gaps, after the American astronomer Daniel Kirkwood, who first explained them in 1866. These gaps occur at orbital distances where an asteroid would complete a simple whole number ratio of orbits compared to Jupiter. For example, at the 3-1 resonance, an asteroid would orbit the Sun exactly 3 times for every one orbit of Jupiter. At these resonant locations, Jupiter's gravitational tugs accumulate over time, gradually increasing the asteroid's orbital eccentricity until it crosses the orbit of Mars or even Earth. The asteroid is then likely to collide with a planet or be ejected from the inner solar system entirely. The Kirkwood gaps are not completely empty, but contain far fewer asteroids than adjacent regions. The 3-1 resonance at about 2.5 astronomical units from the Sun is particularly prominent, as is the 5.2 resonance at about 2.8 astronomical units. These gaps provide clear evidence of Jupiter's powerful gravitational influence on the asteroid belt, an influence that has shaped the belt's structure over billions of years. While most asteroids remain safely within the main belt, some have orbits that bring them closer to the Sun and potentially close to Earth. These near-Earth asteroids, or NEAs, are of particular interest, both scientifically and for planetary defense purposes. Near-Earth asteroids are classified into several groups based on their orbital characteristics. Apollo asteroids have orbits that cross Earth's orbit and have semi-major axes larger than Earth's. Our 10 asteroids also cross Earth's orbit, but have semi-major axes smaller than Earth's. AMA asteroids approach Earth's orbit, but do not cross it, while ATIRA asteroids have orbits entirely inside Earth's orbit. The population of near-Earth asteroids is continually replenished from the main belt. Gravitational interactions, particularly at the Kirkwood gaps, can nudge main belt asteroids onto orbits that bring them into the inner solar system. The Yarkovsky effect, a subtle force caused by the uneven heating and cooling of a rotating asteroid, can also gradually change asteroid orbits over millions of years. Once an asteroid becomes a near-Earth object, its lifetime is relatively short in astronomical terms, typically a few million years before it collides with a planet, falls into the Sun, or is ejected from the inner solar system. The surfaces of asteroids record billions of years of cosmic history. Most asteroids are covered in regolith, a layer of loose, fragmented material created by countless small impacts over the age of the solar system. This regolith can be meters deep on larger asteroids, though smaller asteroids may have little or no regolith due to their weaker gravity. The Japan Aerospace Exploration Agency's Hayabusa 2 mission to asteroid Ryugu revealed a surface covered in boulders and rubble, with very little fine-grained material. The low density of Ryugu suggests it is a rubble pile asteroid, a loose aggregate of fragments held together by gravity rather than a solid monolithic rock. Many asteroids are indeed rubble piles rather than solid bodies. When asteroids collide, they can be shattered into fragments that then reassemble under their mutual gravity, forming loosely bound aggregates with significant internal void space. The asteroid Itokawa, visited by the first Hayabusa mission, has a density suggesting it is about 40% empty space. This rubble pile structure has important implications for planetary defense, as a loosely bound asteroid would respond very differently to deflection attempts than a solid body. Some asteroids have their own moons, small companions orbiting the larger body. The first asteroid moon was discovered in 1993 when the Galileo spacecraft, en route to Jupiter, flew past the asteroid Ida and photographed a tiny moon just 1.4 kilometers across, later named Dactyl. Since then, over 400 asteroid moons have been discovered, including several asteroids with 2 moons and one, the asteroid Sylvia, with 3 known moons. These moons provide valuable information about asteroid masses and densities, properties that are otherwise difficult to measure. The asteroid belt also contains several families of asteroids that share similar orbits and compositions, evidence that they originated from the breakup of larger parent bodies. The Coronis family, for example, consists of hundreds of asteroids with similar orbits, all thought to be fragments of a single asteroid that was shattered by a collision perhaps 2 billion years ago. The Eos family, the Themis family, and many others tell similar stories of ancient catastrophic disruptions. By studying these families, astronomers can piece together the collisional history of the asteroid belt and understand how the population has evolved over time. As we drift through this river of ancient stone, we can appreciate the asteroid belt as a window into the early solar system. These rocky fragments have preserved information about conditions 4.6 billion years ago, information that has been erased on the larger planets by geological activity. The asteroids are not debris or failed planets, but rather a population of small worlds, each with its own history, composition, and story to tell. They are messengers from the dawn of our solar system, patiently waiting for us to read the messages they carry. Now let us turn our attention to the most spectacular visitors in our solar system, the comets. While asteroids are rocky remnants from the warm inner regions of the solar nebula, comets are icy bodies that formed in the cold outer reaches, far from the young sun's heat. When these frozen wanderers venture into the inner solar system, solar radiation transforms them into some of the most beautiful objects in the night sky, trailing glowing tails that can stretch for millions of kilometers. Let us explore the nature of these cosmic snowballs and understand what makes them so different from their rocky asteroid cousins. The fundamental difference between asteroids and comets lies in their composition. While asteroids are primarily rocky and metallic, comets are composed largely of ice mixed with dust and rocky particles. But the ice in comets is not simply frozen water. Cometary ice includes water ice as its primary component, but also contains frozen carbon dioxide, carbon monoxide, methane, ammonia, and a complex mixture of other volatile compounds. These ices formed in the frigid outer regions of the solar nebula, where temperatures were cold enough for these substances to freeze solid. The dust mixed into cometary ice includes silicate minerals similar to those found in asteroids, as well as organic compounds containing carbon, hydrogen, oxygen, and nitrogen. The heart of a comet is called its nucleus, a solid body typically ranging from a few hundred meters to several tens of kilometers across. The largest known comet nucleus belongs to Comet Bernardinelli-Bernstein, discovered in 2021, with a diameter estimated at approximately 137 kilometers. Most comet nuclei are much smaller, with diameters of just a few kilometers being typical. Despite their small size, comet nuclei contain all the material that produces the spectacular displays we observe when comets approach the Sun. When a comet is far from the Sun, in the cold outer reaches of the solar system, its nucleus remains frozen and inactive. The comet appears as nothing more than a faint, star-like point of light, indistinguishable from a small asteroid without careful observation. But as the comet falls inward toward the Sun, solar radiation begins to warm its surface. At distances of roughly 3 to 5 astronomical units from the Sun, approximately the distance of Jupiter's orbit, the surface temperature rises enough for the ices to begin sublimating, transforming directly from solid to gas without passing through a liquid phase. This sublimation marks the awakening of the comet. The gas escaping from the nucleus carries dust particles along with it, creating a cloud of material surrounding the solid core. This cloud is called the coma, from the Latin word for hair, and it can grow to enormous dimensions. While the nucleus might be only a few kilometers across, the coma can expand to diameters of 50,000 to 200,000 kilometers, larger than the planet Jupiter. Despite its vast size, the coma is incredibly diffuse, containing so little material that stars can be seen shining through it. The coma glows partly by reflecting sunlight and partly through fluorescence, as solar ultraviolet radiation excites molecules in the gas and causes them to emit light at specific wavelengths. The most distinctive feature of a comet is its tail, or more accurately, its tails, for most comets display two distinct tails pointing in different directions. The dust tail is composed of small particles released from the nucleus and pushed away from the Sun by the pressure of sunlight itself. This radiation pressure acts more strongly on smaller particles, so the dust tail contains a range of particle sizes being pushed at different rates. The result is a broad curved tail that can appear white or yellowish, the colour of reflected sunlight. Dust tails often show a graceful curve because the dust particles continue to orbit the Sun even as they are pushed outward, creating an arc that traces the comet's recent orbital path. The second tail is the ion tail, also called the gas tail or plasma tail. This tail is composed of ionized gas molecules, atoms and molecules that have lost one or more electrons due to solar ultraviolet radiation. These ions interact with the solar wind, a stream of charged particles constantly flowing outward from the Sun at speeds of several hundred kilometers per second. The solar wind carries magnetic field lines that sweep up the cometary ions and drag them directly away from the Sun. As a result, the ion tail always points almost exactly away from the Sun, regardless of the comet's direction of motion. Ion tails typically appear blue because of emission from ionized carbon monoxide molecules, and they can extend for tens of millions of kilometers, sometimes stretching across a significant fraction of the sky as seen from Earth. The behavior of comet tails leads to one of the most counterintuitive aspects of cometary motion. Because tails are pushed away from the Sun by radiation pressure and solar wind, a comet's tail does not trail behind it like the wake of a boat. Instead, as a comet approaches the Sun, its tail streams out behind it, but as the comet rounds the Sun and begins its outward journey, the tail swings around to point ahead of the comet. The comet essentially backs away from the Sun, leading with its tail rather than following it. This behavior puzzled early observers until the physics of radiation pressure and solar wind were understood. The activity of a comet is not uniform across its surface. Observations from spacecraft that have visited comets reveal that gas and dust erupt from specific active regions rather than from the entire surface. These active regions are areas where fresh ice is exposed to sunlight, allowing sublimation to occur. Much of a comet's surface may be covered by a dark insulating crust of dust and organic material that prevents the underlying ice from receiving enough heat to sublimate. Jets of gas and dust erupt from cracks and vents in this crust, creating dramatic plumes that can be observed from Earth with sufficiently powerful telescopes. The European Space Agency's Rosetta mission, which accompanied Comet 67P Churyumov-Gerasimenko for over 2 years, provided unprecedented views of cometary activity. The spacecraft observed jets erupting from the comet's surface, watched the activity increase as the comet approached the Sun, and documented the complex interplay between solar heating and surface features. The comet's nucleus, shaped like a rubber duck with 2 distinct lobes connected by a narrow neck, rotated every 12 hours, bringing different regions into sunlight and creating a constantly changing pattern of activity. Rosetta's observations revealed that cometary activity is far more complex and variable than simple models had suggested. The composition of cometary material provides crucial information about conditions in the early solar system. Because comets formed in the cold outer regions of the solar nebula and have spent most of their existence in the deep freeze of the outer solar system, they preserve primitive material that has changed little since the solar system's formation. Spectroscopic observations of comets have detected dozens of different molecules in cometary gas, including water, carbon dioxide, carbon monoxide, methane, ammonia, hydrogen sulfide, formaldehyde, methanol, ethane, and hydrogen cyanide. More complex organic molecules have also been detected, including amino acids, the building blocks of proteins. The Rosetta mission's Philae lander, which touched down on the surface of Comet 67P in November 2014, detected 16 organic compounds in the cometary material, including 4 that had never before been detected in a comet. These included acetamide, acetone, methyl isocyanate, and propionaldehyde, compounds that play roles in the chemistry of life. The presence of such complex organic molecules in comets supports the hypothesis that cometary impacts may have delivered some of the chemical building blocks necessary for life to the early Earth. Water ice in comets exists in different forms that reveal information about the temperature at which the ice formed. Ordinary ice, the kind we encounter in daily life, has a crystalline structure with water molecules arranged in a regular hexagonal pattern. But ice that forms at very low temperatures, below about 130 Kelvin, takes an amorphous form, with water molecules arranged randomly rather than in a crystal lattice. Amorphous ice can trap other volatile molecules within its disordered structure, releasing them when the ice is warmed and transforms to the crystalline form. The detection of amorphous ice in comets indicates that the ice formed at very low temperatures, consistent with formation in the cold outer solar system. Comets also contain isotopic signatures that provide clues to their origins. The ratio of deuterium to hydrogen in cometary water has been measured for several comets and shows considerable variation. Deuterium is a heavy isotope of hydrogen, with a nucleus containing one proton and one neutron, rather than just a single proton. The deuterium to hydrogen ratio in a sample of water depends on the temperature and conditions under which the water formed. Some comets have deuterium to hydrogen ratios similar to Earth's oceans, suggesting that cometary impacts could have contributed to Earth's water supply. Other comets have much higher ratios, indicating they formed under different conditions or in different regions of the solar nebula. The surfaces of comet nuclei are among the darkest objects in the solar system, reflecting only about 4% of the sunlight that falls on them. This darkness comes from the layer of organic material and dust that accumulates on the surface as volatile ices sublimate away. The organic compounds in this surface layer are rich in carbon and have been darkened by billions of years of exposure to cosmic radiation. When spacecraft have photographed comet nuclei up close, they have revealed surfaces that are almost coal black, far darker than the bright white appearance we might expect from bodies made largely of ice. The shapes of comet nuclei are often irregular and elongated, reflecting their formation through the gentle accumulation of smaller icy bodies in the outer solar system. Comet 67P Churyumov-Gerasimenko has its distinctive two-lobed shape, possibly formed when two separate bodies gently collided and stuck together billions of years ago. Comet Halley's nucleus is roughly potato-shaped, measuring about 15 kilometers long and 8 kilometers wide. Comet Borrelly, visited by NASA's Deep Space One mission, resembles a bowling pin. These irregular shapes are typical of small bodies that never experienced enough gravity to pull themselves into spherical forms. The density of comet nuclei is surprisingly low, typically about half the density of water ice. This low density indicates that comet nuclei are highly porous, with significant void space between the ice and dust particles. Some estimates suggest that comet nuclei may be as much as 70 to 80% empty space, making them extremely fragile structures. This fragility explains why comets sometimes break apart, either through tidal forces when passing close to the Sun or a planet, or simply through the stresses of outgassing as volatile ices sublimate unevenly. Comets gradually lose mass with each passage through the inner solar system. Every time a comet approaches the Sun, solar heating drives off tons of gas and dust, material that is lost forever into space. A typical comet might lose a layer of material several meters thick during each perihelion passage, its closest approach to the Sun. Over many orbits, this mass loss can dramatically reduce a comet's size or even completely exhaust its volatile content. Comets that have lost all their volatile material may continue to orbit the Sun as inert asteroid-like bodies, sometimes called extinct comets or dead comets. The lifetime of a comet in the inner solar system is therefore limited. Short-period comets, those with orbital periods of less than 200 years, may survive for only a few thousand perihelion passages before exhausting their volatiles or breaking apart. This might seem like a long time, but it is brief compared to the 4.5 billion year age of the solar system. The continued presence of short-period comets in the inner solar system indicates that the population must be continuously replenished from reservoirs in the outer solar system, a topic we will explore in detail shortly. Some comets meet dramatic ends rather than slowly fading away. Comet Shoemaker-Levy 9, discovered in 1993, had been captured into orbit around Jupiter and was torn apart by tidal forces during a close approach to the giant planet. The comet fragmented into at least 21 pieces, which then crashed into Jupiter's atmosphere in July 1994 in one of the most spectacular astronomical events ever witnessed. The impacts created dark scars in Jupiter's atmosphere larger than Earth, visible through backyard telescopes for months afterward. This event demonstrated both the fragility of comet nuclei and the potential consequences of cometary impacts on planets. The transformation of a dormant, frozen nucleus into an active, tailed comet is one of nature's most beautiful metamorphoses. A comet spends most of its existence as an inert chunk of ice and rock, invisible except to the most powerful telescopes. But when orbital mechanics bring it close to the Sun, it awakens into glorious activity, sprouting a coma and tails that can span millions of kilometers. For a few weeks or months, it graces our skies before retreating once again into the darkness from which it came. This cycle of dormancy and activity, repeated over thousands or millions of years, gradually depletes the comet until nothing remains but dust scattered along its orbital path. Yet even in death, comets continue to make their presence known, as we shall see when we discuss meteor showers later in our journey. Having explored the nature of comets themselves, let us now venture to the distant realms where most comets spend the vast majority of their existence. Beyond the orbit of Neptune, in the cold darkness at the edge of our solar system, lie two great reservoirs of icy bodies that supply the comets we observe in the inner solar system. These regions, the Kuiper Belt and the Oort Cloud, contain billions of frozen worlds that have remained largely unchanged since the formation of the solar system. Let us journey outward into these remote territories and discover what lies in the outer darkness. The Kuiper Belt begins just beyond the orbit of Neptune, at a distance of approximately 30 astronomical units from the Sun, and extends outward to perhaps 50 or 60 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. So the inner edge of the Kuiper Belt lies roughly 4.5 billion kilometers from the Sun. At this distance, sunlight is so faint that noon would appear no brighter than deep twilight on Earth, and temperatures hover around 40 Kelvin, more than 230 degrees Celsius below zero. The existence of the Kuiper Belt was predicted long before it was observed. In 1951, the Dutch-American astronomer Gerard Kuiper suggested that a belt of icy bodies might exist beyond Neptune, remnants of the solar nebula that never coalesced into a planet. However, Kuiper believed that Pluto's gravity would have cleared this region, so he did not expect many objects to remain. Other astronomers, including Kenneth Edgeworth in 1943 and Fred Whipple in 1964, made similar predictions. The region is sometimes called the Edgeworth-Kuiper Belt, in recognition of these multiple contributors to the concept. The first Kuiper Belt object, other than Pluto, was not discovered until 1992, when astronomers David Jewett and Jane Liu detected a small body designated 1992 QB1, later named Albion. This discovery confirmed the existence of the Kuiper Belt and opened a new frontier in solar system exploration. In the decades since, astronomers have discovered thousands of Kuiper Belt objects, with estimates suggesting the total population numbers in the hundreds of thousands for objects larger than 100 kilometers in diameter, and billions for smaller bodies. Pluto, discovered in 1930 and long considered the ninth planet, is now recognized as one of the largest members of the Kuiper Belt population. The discovery of other large Kuiper Belt objects, particularly Eris in 2005, which is nearly the same size as Pluto, prompted the International Astronomical Union to reconsider Pluto's planetary status. In 2006, the IAU created the category of dwarf planets and reclassified Pluto accordingly. While this decision remains controversial among some members of the public, it reflects the scientific understanding that Pluto is part of a larger population of similar objects rather than a unique body, like the 8 major planets. The Kuiper Belt is not uniformly distributed, but shows distinct structure reflecting the gravitational influence of Neptune. The classical Kuiper Belt, sometimes called the Cubewano population after the prototype object 1992 QB1, consists of objects with relatively circular orbits that do not approach Neptune closely. These objects occupy the region between about 42 and 48 astronomical units from the Sun, beyond Neptune's direct gravitational influence. The resonant populations are Kuiper Belt objects, whose orbital periods are simple fractions of Neptune's orbital period. The most famous resonant population is the Plutinos, objects in the 3.2 resonance with Neptune, meaning they complete exactly 2 orbits for every 3 orbits Neptune completes. Pluto is the largest Plutino, and the resonance protects these objects from close encounters with Neptune despite their orbits crossing Neptune's orbital distance. Other resonant populations exist at the 2, 1, 5, 3 and 403 resonances, among others. The scattered disk is a population of objects with highly elliptical orbits that can take them from near Neptune's orbit out to hundreds of astronomical units from the Sun. These objects were likely scattered outward by gravitational interactions with Neptune during the early history of the solar system. The scattered disk is thought to be the primary source of short-period comets, as gravitational perturbations can occasionally nudge scattered disk objects onto orbits that bring them into the inner solar system. Eris, the largest known scattered disk object, has an orbit that takes it from 38 astronomical units at its closest approach to the Sun, out to 97 astronomical units at its most distant. At its current distance of about 96 astronomical units, Eris is one of the most distant known objects in the solar system. Eris is slightly smaller than Pluto, but more massive, indicating a higher density and possibly a different composition. Eris has one known moon, Dysnomia, discovered in 2005. The composition of Kuiper Belt objects varies considerably. Spectroscopic observations have detected water ice, methane ice, nitrogen ice, and various organic compounds on the surfaces of different objects. Pluto's surface is dominated by nitrogen ice, with smaller amounts of methane and carbon monoxide ice. Eris appears to have a surface rich in methane ice that has been chemically altered by cosmic radiation. Smaller Kuiper Belt objects show a range of colours from neutral grey to deep red, with the red colours attributed to complex organic compounds called tholins, formed by radiation processing of simpler molecules. The New Horizons spacecraft, which flew past Pluto in July 2015, revealed a world of unexpected complexity and beauty. Pluto's surface displays a remarkable variety of terrains, including vast plains of nitrogen ice, towering mountains of water ice, and possible cryovolcanoes that may erupt slushy mixtures of water, ammonia, and methane. The heart-shaped feature, informally named Tombor Regio, after Pluto's discoverer Clyde Tombor, contains a vast glacier of nitrogen ice called Sputnik Planitia that appears to be geologically active, with convection cells slowly churning the ice over millions of years. After its Pluto encounter, New Horizons continued outward to visit a small Kuiper Belt object named Arakoth, formerly known as 2014 MU69, and nicknamed Ultima Thule. This flyby in January 2019 provided the first close-up images of a small primitive Kuiper Belt object. Arakoth proved to be a contact binary, two roughly spherical lobes joined together in a shape resembling a snowman. The smooth, lightly cratered surface suggests that Arakoth formed through the gentle merging of two separate objects rather than through violent collision, providing insights into how planetesimals accumulated in the early solar system. Far beyond the Kuiper Belt, at distances so vast they strain comprehension, lies the Oort Cloud. This spherical shell of icy bodies is thought to extend from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun, or nearly 2 light-years. At these distances, the Sun appears as merely the brightest star in the sky, providing negligible warmth. Objects in the Oort Cloud are so loosely bound to the Sun that the gravitational influence of passing stars and the overall gravitational field of the Milky Way galaxy can significantly affect their orbits. The Oort Cloud has never been directly observed. No telescope has ever detected an individual Oort Cloud object in its distant home. Our knowledge of the Oort Cloud comes entirely from studying the comets that occasionally fall from this remote reservoir into the inner solar system. By analysing the orbits of long-period comets, those with orbital periods greater than 200 years, astronomers can trace their origins back to the Oort Cloud. The orbital characteristics of these comets, particularly their random orbital inclinations and their extremely elongated orbits, point to a spherical source region at vast distances from the Sun. The Dutch astronomer Jan Oort first proposed the existence of this distant comet reservoir in 1950. Oort noticed that long-period comets seem to come from all directions in space, not just from the plane of the solar system where the planets orbit. He also noticed that many long-period comets had orbits suggesting they were making their first visit to the inner solar system, with Ophelia, their most distant points from the Sun, clustering around 20,000 astronomical units. Oort proposed that a vast spherical cloud of comets surrounds the solar system at this distance, and that gravitational perturbations from passing stars occasionally send some of these comets falling inward toward the Sun. The total population of the Oort Cloud is estimated to be in the trillions of objects, though this number is highly uncertain. If we count only objects larger than 1 kilometre in diameter, estimates range from several hundred billion to a few trillion. The total mass of the Oort Cloud is probably several times the mass of Earth, though again with large uncertainties. Despite containing trillions of objects, the Oort Cloud is so vast that the average distance between objects is tens of millions of kilometres. If you were somehow transported to the Oort Cloud, you would see nothing but empty space and distant stars, with the Sun appearing as just another bright star among thousands. The objects in the Oort Cloud did not form at their current locations. Computer simulations of solar system formation indicate that the Oort Cloud was populated by icy planetesimals that originally formed in the region of the giant planets, between roughly 5 and 30 astronomical units from the Sun. As the giant planets grew and migrated during the early solar system, their gravitational interactions scattered countless small bodies outward. Some were ejected from the solar system entirely, but others were thrown into extremely elongated orbits that took them to the outer reaches of the Sun's gravitational influence. Over time, gravitational perturbations from passing stars and the galactic tide circularized these orbits and randomized their orientations, creating the spherical Oort Cloud we infer today. The inner Oort Cloud, sometimes called the Hills Cloud, after the astronomer Jack Hills, who proposed its existence, may contain a denser population of objects at distances of roughly 2,000 to 20,000 astronomical units. This inner region would be less affected by stellar perturbations than the outer Oort Cloud and might contain a significant fraction of the total Oort Cloud mass. The inner Oort Cloud may be the source of some long-period comets, particularly those with orbital periods of thousands rather than millions of years. The Oort Cloud represents the outer boundary of our solar system, the region where the Sun's gravity becomes comparable to the gravitational influences of other stars and the galaxy as a whole. Beyond the Oort Cloud lies interstellar space, the vast emptiness between the stars. Yet even this boundary is not absolute. The Sun is moving through the galaxy, and over millions of years it passes relatively close to other stars. These stellar encounters can strip objects from the outer Oort Cloud, sending some into interstellar space while capturing others from the Oort clouds of passing stars. The Oort Cloud is thus a dynamic structure, slowly exchanging material with the broader galactic environment. The discovery of interstellar objects passing through our solar system has added a new dimension to our understanding of these distant reservoirs. In 2017, astronomers detected an object designated 1I Oumuamua, the first confirmed interstellar visitor. Oumuamua's hyperbolic orbit indicated it originated from outside our solar system, passing through at high speed before continuing on its journey through interstellar space. In 2019, a second interstellar object, 2I Borisov, was discovered, and this one was clearly a comet, displaying a coma and tail as it passed through the inner solar system. These interstellar visitors may be objects ejected from the Oort clouds of other stars, providing our first glimpses of material from other planetary systems. As we contemplate these vast reservoirs of frozen worlds, we gain a new appreciation for the scale of our solar system. The planets, which seem so distant from our earthly perspective, occupy only a tiny fraction of the Sun's gravitational domain. The Kuiper Belt extends the known solar system to 50 or 60 astronomical units, but the Oort Cloud reaches out nearly 2 light-years, almost halfway to the nearest star. In these remote regions, trillions of icy bodies orbit in frozen silence, occasionally disturbed by gravitational nudges that send them falling inward toward the distant warmth of the Sun. When we observe a comet gracing our night sky, we are seeing a visitor from these outer reaches, a frozen time capsule that has journeyed billions of kilometers to briefly illuminate our heavens before returning to the darkness from which it came. Throughout human history, certain comets have captured the imagination of entire civilizations, inspiring awe, fear, scientific discovery, and cultural transformation. These famous visitors have marked turning points in history, accompanied the births and deaths of kings, and driven advances in our understanding of the cosmos. Let us now explore some of the most renowned comets ever to grace Earth's skies, from ancient times to the present day. No comet is more famous than Halley's Comet, the first comet recognized as a periodic visitor to the inner solar system. We have already encountered Edmund Halley's brilliant deduction that the comets of 1531, 1607 and 1682 were the same object returning at regular intervals. But the story of Halley's Comet extends far beyond this scientific breakthrough, reaching back through recorded history and touching countless human lives across millennia. Chinese astronomers recorded an appearance of Halley's Comet in 240 BCE, making it one of the earliest documented observations of this famous visitor. The comet appeared again in 164 BCE and 87 BCE, with each apparition carefully noted in Chinese historical records. Babylonian astronomers also observed the comet, with clay tablets recording its appearance in 164 BCE. These ancient observations, preserved across thousands of years, have allowed modern astronomers to trace Halley's orbital history and refine calculations of its past and future appearances. The 66 CE apparition of Halley's comet coincided with the Jewish revolt against Roman rule that culminated in the destruction of the Temple in Jerusalem in 70 CE. The Roman historian Josephus recorded the comet as one of several portents that preceded this catastrophe. Whether the comet actually influenced events or was simply remembered because of the disaster that followed, the association between Halley's comet and historical upheaval was established early. The 1066 apparition of Halley's comet is perhaps the most famous in Western history, immortalised in the Bayeux Tapestry depicting the Norman conquest of England. The tapestry shows the comet blazing above a group of anxious observers, with the Latin inscription Isti mirant stellum, meaning, "These men wonder at the star." King Harold II of England, who would die at the Battle of Hastings later that year, is shown receiving news of the comet's appearance. For the Normans, the comet was a favourable omen presaging their victory. For the English, it was a harbinger of doom. The same comet, interpreted in opposite ways by the two sides of a conflict, illustrates how human meaning has always been projected onto these celestial visitors. The 1301 apparition of Halley's comet was observed by the Italian painter Giotto di Bondone, who incorporated its image into his famous fresco Adoration of the Magi in the Scrovegni Chapel in Padua. Giotto depicted the Star of Bethlehem as a realistic comet with a golden tail, the first naturalistic representation of a comet in Western art. The European Space Agency later honoured this connection by naming its mission to Halley's comet Giotto. The 1456 apparition occurred during a period of great anxiety in Europe, as Ottoman forces had conquered Constantinople just 3 years earlier and were advancing into the Balkans. Pope Calixtus III allegedly ordered prayers and church bells to ward off the comet, which was seen as an omen of Turkish victory. While some details of this story may be legendary, the association of the comet with fears of invasion reflects the cultural climate of the time. The 1682 apparition was the one that Edmund Halley himself observed, leading to his groundbreaking analysis. Halley's successful prediction of the comet's 1758 return, confirmed 16 years after his death, established cometary astronomy as a predictive science and demonstrated the power of Newtonian mechanics to explain celestial phenomena. The 1835 apparition was notable for being the first appearance of Halley's comet to be photographed, though the technology was too primitive to capture useful images. The American author Mark Twain was born 2 weeks after the comet's closest approach to Earth, in November 1835. Twain later wrote that he came in with the comet and expected to go out with it, a prediction that proved eerily accurate when he died on April 21st, 1910, one day after the comet's closest approach during its next apparition. The 1910 apparition of Halley's comet was one of the most spectacular in recent centuries, with the comet passing relatively close to Earth and displaying a tail that stretched across much of the sky. This apparition also caused widespread public fear due to the announcement that spectroscopic analysis had detected cyanogen gas in the comet's tail. When astronomers calculated that Earth would pass through the comet's tail on May 19, 1910, some newspapers reported that the cyanogen might poison Earth's atmosphere. Entrepreneurs sold comet pills and anti-comet umbrellas to frighten citizens, while some people sealed their homes against the supposed poison gas. In reality, the gas in a comet's tail is so diffuse that it has no measurable effect on Earth's atmosphere, and the passage through the tail went entirely unnoticed. The 1986 apparition of Halley's Comet was the first to be visited by spacecraft. An international armada of 5 spacecraft from the Soviet Union, Japan and Europe flew past the comet, with the European Space Agency's Giotto mission passing within 596 kilometers of the nucleus. These spacecraft returned the first close-up images of a comet nucleus, revealing a dark potato-shaped body about 15 kilometers long, with jets of gas and dust erupting from active regions on the sunlit side. The 1986 apparition was geometrically unfavourable for Earth-based observers, with the comet remaining relatively distant and appearing less spectacular than in 1910, but the scientific returns from the spacecraft encounters more than compensated. Halley's Comet will next return to the inner solar system in 2061, when it will be more favourably positioned for observation from Earth. Those who witness this apparition will be continuing a tradition of comet watching that stretches back thousands of years, connecting them to countless generations of human observers who have gazed upon the same celestial visitor. The Great Comet of 1811 was one of the most spectacular comets of the 19th century, visible to the naked eye for approximately 9 months, a record that stood for over 2 centuries. The comet's coma was estimated to be larger than the Sun, making it one of the largest cometary atmospheres ever observed. The 1811 comet appeared during the build-up to Napoleon's invasion of Russia, and both sides interpreted it as an omen favouring their cause. In Leo Tolstoy's novel War and Peace, the character Pierre Bezukhov observes the comet and sees it as a symbol of his own spiritual transformation. The comet also gave its name to a legendary vintage of wine, as the grape harvest of 1811 was exceptionally good, and wines from that year were marketed as comet wine for decades afterward. The Great Comet of 1843 was remarkable for its extremely close approach to the Sun, passing within 830,000 kilometres of the solar surface, so close that it was visible in daylight near the Sun. The comet's tail stretched for over 300 million kilometres, the longest comet tail ever measured at that time. This comet was a member of the Kreutz Sungrazer family, a group of comets that share similar orbits and are thought to be fragments of a single large comet that broke apart centuries or millennia ago. Comet Donati, which appeared in 1858, is considered one of the most beautiful comets ever observed. Its gracefully curved dust tail and prominent ion tail made it a favourite subject for artists and photographers. Photographs of Comet Donati were among the first successful comet photographs, though the technology of the time limited their quality. The comet inspired numerous artistic depictions and helped establish the popular image of what a comet should look like. The Great Comet of 1882 was another spectacular Kreutz sungrazer that became bright enough to be visible in daylight near the Sun. After its perihelion passage, the comet's nucleus was observed to split into multiple fragments, providing early evidence for the fragility of comet nuclei. The comet remained visible to the naked eye for several months and was extensively photographed, with some images revealing intricate structure in the tail. Comet Hyakutake, discovered in January 1996, passed unusually close to Earth in March of that year, approaching within 15 million kilometres, about 40 times the Earth-Moon distance. This close approach made Hyakutake one of the most spectacular comets of the 20th century, with a tail stretching over 100 degrees across the sky under dark conditions. The comet's passage provided an opportunity for detailed observations of cometary chemistry and structure, with X-ray emissions detected from a comet for the first time. Comet Hale-Bopp, discovered independently by Alan Hale and Thomas Bopp in July 1995, became one of the most widely observed comets in history during its 1997 apparition. The comet was exceptionally large, with a nucleus estimated at up to 40 kilometers in diameter, and it was visible to the naked eye for a record 18 months, surpassing the Great Comet of 1811. Hale-Bopp displayed both a prominent dust tail and a distinct blue ion tail, making it a spectacular sight even from light-polluted urban areas. The comet's long visibility allowed millions of people to observe it, including many who had never seen a comet before. Tragically, Hale-Bopp was also associated with the Heaven's Gate cult mass suicide in March 1997, a reminder that comets can still inspire irrational beliefs in the modern era. Comet McNaught, which appeared in early 2007, was the brightest comet in over 40 years, reaching a peak magnitude of approximately negative 5.5, bright enough to be visible in daylight. The comet was best observed from the southern hemisphere, where it displayed a spectacular fan-shaped dust tail that spread across a significant portion of the evening sky. Observers in Australia, South America, and Southern Africa were treated to views that many described as the most beautiful cometary display they had ever witnessed. The tail showed remarkable striations, parallel bands of dust that created an almost feathered appearance against the twilight sky. Northern Hemisphere observers had a more limited view, catching glimpses of the comet low on the horizon during its brief period of maximum brightness. Comet Lovejoy, discovered by Australian amateur astronomer Terry Lovejoy in November 2011, provided one of the most dramatic cometary events of recent years. This comet was a Kreutz sungrazer, a member of the family of comets that pass extremely close to the Sun. Astronomers expected Comet Lovejoy to be destroyed during its perihelion passage, as it would pass through the Sun's corona at a distance of only about 140,000 kilometers from the solar surface. Remarkably, the comet survived its close encounter, emerging from behind the Sun with its tail streaming behind it. Solar observatories captured stunning footage of the comet plunging toward the Sun and then reappearing on the other side, a testament to the resilience of at least some comet nuclei. Comet Lovejoy went on to become a beautiful object in southern hemisphere skies during December 2011, with a long, graceful tail visible before dawn. Comet Ison, discovered in September 2012 by Russian astronomers Vitaly Nevsky and Artyom Novichenok, generated tremendous excitement and anticipation as it approached the Sun in late 2013. Early predictions suggested that Ison might become exceptionally bright, potentially visible in daylight, and rivaling the Moon in brilliance. The comet was making its first visit to the inner solar system from the Oort Cloud, meaning its surface was pristine and rich in volatile ices that had never been exposed to solar heating. As Ison approached the Sun, however, it became clear that the comet was not brightening as rapidly as hoped. On November 28, 2013, Ison passed within 1.2 million kilometers of the Sun's surface. Solar observatories watched as the comet appeared to disintegrate during its perihelion passage, with only a faint remnant emerging on the other side. Within days, even this remnant had faded from view. Ison's demise was a disappointment for those hoping for a spectacular display, but it provided valuable scientific data about the behavior of comets during close solar approaches. Comet Neowise, discovered by NASA's Near-Earth Object, Wide-Field Infrared Survey Explorer spacecraft in March 2020, became the brightest comet visible from the Northern Hemisphere in over 2 decades. The comet reached naked-eye visibility in July 2020, appearing in the pre-dawn sky with a distinctive dust tail and fainter ion tail. For many observers confined to their homes during the COVID-19 pandemic, Comet Neowise provided a welcome celestial distraction and an opportunity to witness a natural wonder. The comet was widely photographed, with images showing it above landmarks around the world. NEOWISE demonstrated that spectacular comets can still appear with little warning, delighting observers who happen to be watching the sky at the right time. The Great Comet of 1680, also known as Kirch's Comet, after the German astronomer Gottfried Kirch, who first observed it, was one of the brightest comets of the 17th century and played an important role in the development of cometary science. Isaac Newton used observations of this comet to demonstrate that comets follow the same laws of motion as planets, moving along conic section orbits under the influence of the Sun's gravity. Newton's analysis, published in his Principia Mathematica in 1687, established the theoretical framework that Edmund Halley would later use to predict the return of the comet that bears his name. The Great Comet of 1680 thus marks a turning point in human understanding, the moment when comets were transformed from mysterious omens into objects whose behaviour could be predicted and explained through mathematical physics. Comet Encke holds the distinction of having the shortest orbital period of any known comet, completing one orbit around the Sun every 3.3 years. The comet is named after the German astronomer Johann Franz Encke, who calculated its orbit in 1819 and recognized that comets observed in 1786, 1795, 1805, and 1818 were all the same object. Encke's comet has been observed on more returns than any other comet, with records of over 60 apparitions. Because of its short orbital period and frequent passages through the inner solar system, Encke's comet has lost much of its volatile material and is now relatively faint, rarely visible to the naked eye. The comet is associated with the Taurid meteor shower, and some researchers have suggested that Encke is the remnant of a much larger comet that broke apart thousands of years ago, with the Taurid meteor stream representing debris from this ancient disruption. Comet Shoemaker-Levy 9, while never visible as a traditional comet with a tail, became one of the most famous comets of the 20th century due to its spectacular demise. Discovered in March 1993 by Eugene and Carolyn Shoemaker and David Levy, the comet had been captured into orbit around Jupiter and had been torn apart by tidal forces during a close approach to the giant planet in July 1992. When discovered, the comet appeared as a string of fragments, described by one astronomer as resembling a string of pearls. Calculations showed that these fragments would collide with Jupiter in July 1994, providing the first opportunity to observe a collision between two solar system bodies. The impacts exceeded all expectations, creating dark scars in Jupiter's atmosphere larger than Earth that remained visible for months. The Shoemaker-Levy 9 impacts demonstrated the potential consequences of cometary impacts and helped stimulate interest in planetary defense against near-Earth objects. The Great September Comet of 1882 was a spectacular Kreuz grazer that became bright enough to be visible in daylight near the Sun. After perihelion, the comet's nucleus was observed to split into at least 4 fragments, providing dramatic evidence of the fragility of comet nuclei. The comet remained visible to the naked eye for several months and was extensively photographed, with images revealing complex structure in the tail. This comet may have been a fragment of an even larger comet that broke apart in 1106, and its own fragments may return as separate comets in the coming centuries. Comet West, which appeared in 1976, was one of the finest comets of the 20th century, though it received relatively little public attention due to conservative predictions from astronomers wary of overpromising after the disappointing apparition of Comet Kohoutek in 1973. Comet West displayed a spectacular fan-shaped dust tail and was visible in the pre-dawn sky for several weeks. The comet's nucleus split into 4 fragments after perihelion, an event captured in photographs that showed the fragments separating over several days. Those who made the effort to observe Comet West were rewarded with one of the most beautiful cometary displays of the century. These famous comets represent only a small fraction of the thousands of comets that have been observed throughout human history. Each comet carries its own story, its own journey from the frozen outer reaches of the solar system to the warmth of the inner planets, and back again. Some comets return regularly, like old friends visiting on a predictable schedule. Others appear once and never return, their elongated orbits carrying them back into the depths of space for millions of years. Whether bright or faint, returning or one-time visitors, each comet connects us to the vast reservoir of icy bodies that surrounds our solar system and to the primordial material from which our planetary system formed. While comets capture attention with their spectacular tails and dramatic appearances, asteroids have their own fascinating stories to tell. From the largest bodies in the asteroid belt to the small rocks that occasionally pass close to Earth, these rocky remnants of the early solar system have revealed secrets about planetary formation, delivered samples to our laboratories, and reminded us of the potential hazards lurking in our cosmic neighbourhood. Let us explore some of the most notable asteroids and near-Earth objects that have shaped our understanding of these ancient wanderers. Ceres, the largest object in the asteroid belt, deserves special attention as the first asteroid ever discovered and the only dwarf planet in the inner solar system. With a diameter of approximately 940 kilometres, Ceres contains about one-third of the total mass of the asteroid belt. Unlike most asteroids, Ceres is large enough for its own gravity to have pulled it into a roughly spherical shape, a key criterion for dwarf planet status. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, revealing a world of unexpected complexity and intrigue. Dawn's observations showed that Ceres has a differentiated interior, with a rocky core surrounded by a mantle that may contain significant amounts of water ice. The surface displays a variety of geological features, including impact craters, mountains, and mysterious bright spots that puzzled scientists when first observed from a distance. These bright spots, concentrated in the crater Okator, proved to be deposits of sodium carbonate, a type of salt. The presence of these salts suggests that briny water has reached the surface from a subsurface reservoir, possibly through cryovolcanic processes. Ceres may harbour a subsurface ocean of liquid water, making it a potential target for future astrobiological exploration. The mountain Ahuna Mons on Ceres rises about 5 kilometres above the surrounding terrain and appears to be a cryovolcano, a volcano that erupts water, ammonia, and other volatiles rather than molten rock. Ahuna Mons is remarkably young by geological standards, perhaps only a few 100 million years old, suggesting that Ceres may still be geologically active. The discovery of recent geological activity on a body in the asteroid belt was unexpected and has changed our understanding of what small bodies in the solar system are capable of. Vesta, the second largest object in the asteroid belt, with a diameter of about 525 kilometres, is a very different world from Ceres. While Ceres is rich in water and appears relatively primitive, Vesta is a dry, rocky body that experienced significant heating and differentiation early in its history. Vesta has a metallic iron-nickel core, a rocky mantle, and a basaltic crust, making it more similar in structure to the terrestrial planets than to most asteroids. The Dawn spacecraft visited Vesta from 2011 to 2012 before continuing on to Ceres, providing detailed maps of its surface and composition. Vesta's most prominent feature is a massive impact basin near its south pole called Rhea Silvia, approximately 505 kilometres in diameter and 19 kilometres deep. This basin was created by a catastrophic impact that excavated about 1% of Vesta's total volume and sent fragments flying into space. Many of these fragments eventually made their way to Earth as meteorites, and we can identify them by their distinctive composition. The Herde meteorites, named for the three types Howardites, Eucrites, and Diogenites, are believed to originate from Vesta, giving us samples of this distant world without the need for a sample return mission. Psyche, a metallic asteroid approximately 226 kilometers in diameter, represents one of the most intriguing targets in the asteroid belt. Psyche appears to be composed primarily of iron and nickel, the same metals that make up Earth's core. One hypothesis suggests that Psyche is the exposed core of a protoplanet that was stripped of its rocky mantle by violent collisions early in solar system history. If this hypothesis is correct, Psyche offers a unique opportunity to study the interior of a planetary body, material that is normally buried thousands of kilometers beneath a planet's surface and completely inaccessible to direct observation. NASA's Psyche mission, launched in October 2023, is currently en route to this metallic world and will arrive in 2029. The spacecraft will orbit Psyche for approximately 2 years, mapping its surface, measuring its gravity field, and determining its composition. If Psyche is indeed a planetary core, it will provide insights into the violent collisions that shaped the early solar system and the processes that created the iron cores of terrestrial planets like Earth. Bennu, a small near-Earth asteroid approximately 500 meters in diameter, became one of the most thoroughly studied asteroids in history when NASA's OSIRIS-REx spacecraft visited it from 2018 to 2021. Bennu is a carbonaceous asteroid, dark and rich in organic compounds, representing primitive material from the early solar system. The spacecraft spent over 2 years mapping Bennu's surface in exquisite detail before collecting a sample of surface material in October 2020. The sample collection was a dramatic event. OSIRIS-REx descended to Bennu's surface and extended a collection arm that touched the asteroid for approximately 6 seconds while firing a burst of nitrogen gas to stir up loose material. The spacecraft collected far more material than expected, so much that some was escaping from the overfilled collection chamber. The sample, totaling approximately 121 grams, was returned to Earth in September 2023, landing in the Utah deserts. Analysis of the Bennu sample has revealed the presence of water-bearing minerals, organic compounds, and even amino acids, supporting the hypothesis that asteroids like Bennu may have delivered some of the building blocks of life to the early Earth. Ryugu, another carbonaceous near-Earth asteroid, was visited by Japan's Hayabusa 2 spacecraft from 2018 to 2019. Ryugu is slightly larger than Bennu, with a diameter of about 900 meters, and has a distinctive spinning top shape with a prominent equatorial ridge. Like Bennu, Ryugu proved to be a rubble pile asteroid, a loose aggregate of boulders and smaller fragments held together by gravity rather than material strength. The surface was rougher than expected, covered in boulders with very little fine-grained material, which complicated the sample collection process. Hayabusa 2 collected samples from 2 locations on Ryugu, including material excavated from beneath the surface by an impactor that created an artificial crater. The samples, totaling about 5.4 grams, were returned to Earth in December 2020. Analysis has revealed that Ryugu's material is among the most primitive ever studied, with a composition similar to the Sun and containing water, organic compounds, and pre-solar grains that formed before our solar system existed. The Ryugu samples complement the Bennu samples, providing material from 2 different carbonaceous asteroids for comparison. Itokawa, a small near-Earth asteroid visited by Japan's original Hayabusa mission in 2005, was the first asteroid from which samples were returned to Earth. Itokawa is an S-type asteroid, composed primarily of silicate minerals rather than the carbon-rich material of Bennu and Ryukyu. The asteroid is elongated, measuring about 535 meters long and 209 meters wide, and has a distinctive peanut shape, suggesting it may be a contact binary formed from two separate bodies that gently merged. Hayabusa's sample return, though it collected only about 1,500 tiny grains due to a malfunction in the collection system, demonstrated that asteroid sample return was technically feasible and paved the way for the more ambitious OSIRIS-REx and Hayabusa 2 missions. Apophis, discovered in 2004, briefly held the record for the highest impact probability ever calculated for a known asteroid. Initial observations suggested a 2.7% chance that Apophis would strike Earth on April 13, 2029, which would have been a catastrophic event given the asteroid's estimated diameter of about 370 meters. Subsequent observations refined the orbit and ruled out any impact in 2029, though Apophis will pass remarkably close to Earth on that date, coming within about 31,000 kilometers of the surface, closer than the orbits of geosynchronous satellites. This close approach will be visible to the naked eye from parts of Europe, Africa, and Western Asia, as Apophis will briefly become a third-magnitude object moving rapidly across the sky. The 2029 close approach will provide an unprecedented opportunity to study a potentially hazardous asteroid up close. Earth's gravity will significantly alter Apophis's orbit during the encounter, and scientists will be able to observe how the asteroid responds to tidal forces. Several space agencies are considering missions to Apophis around the time of its close approach, which would provide detailed information about its composition, structure, and rotation. Didymos and Dimorphos became famous in September 2022 when NASA's DART spacecraft deliberately crashed into Dimorphos, the smaller moon of the binary asteroid system, in the first test of planetary defense technology. Didymos is approximately 780 meters in diameter, while Dimorphos is about 160 meters across. Before the impact, Dimorphos orbited to Didymos every 11 hours and 55 minutes. The DART impact successfully changed this orbital period by about 33 minutes, demonstrating that kinetic impactor technology can alter the orbit of an asteroid. This technique could potentially be used to deflect a hazardous asteroid discovered on a collision course with Earth, given sufficient warning time. The European Space Agency's Hera mission, launched in October 2024, will arrive at the Didymos system in late 2026 to conduct a detailed post-impact investigation. Hera will measure the mass of Dimorphos, examine the impact crater created by DART, and study how the impact affected the asteroid's structure and orbit. This follow-up investigation will provide crucial information for refining planetary defense strategies. Eros, a near-Earth asteroid approximately 34 kilometers long, was the first asteroid to be orbited by a spacecraft when NASA's Near-Shoemaker mission arrived in February 2000. The spacecraft spent a year orbiting Eros, mapping its surface in detail and measuring its gravity field, before making a controlled descent to the surface in February 2001. Although not designed as a lander, Near-Shoemaker survived the touchdown and transmitted data from the surface for about 2 weeks. Eros is an S-type asteroid with an elongated, irregular shape, covered in craters and boulders. The detailed observations from Near-Shoemaker revealed that Eros is a consolidated body rather than a rubble pile, with a relatively uniform interior. Ida and Dactyl became famous in 1993 when the Galileo spacecraft, en route to Jupiter, flew past Ida and discovered that it had a tiny moon. Dactyl, only about 1.4 kilometers across, was the first asteroid moon ever discovered. The discovery demonstrated that even small asteroids can have natural satellites and opened a new field of asteroid moon studies. Since then, over 400 asteroid moons have been discovered, revealing that binary and multiple asteroid systems are common throughout the solar system. The Chelyabinsk meteor, which exploded over Russia on February 15, 2013, provided a dramatic reminder that asteroid impacts are not merely historical events, but ongoing hazards. The object that caused the Chelyabinsk event was approximately 20 meters in diameter, far too small to be detected by existing asteroid surveys before it entered Earth's atmosphere. The explosion released energy equivalent to about 500 kilotons of TNT, roughly 30 times the energy of the Hiroshima atomic bomb. The shockwave from the explosion damaged thousands of buildings and injured approximately 1,500 people, mostly from flying glass. Remarkably, no one was killed, largely because the explosion occurred at high altitude and the energy was distributed over a wide area. The Chelyabinsk event occurred on the same day that asteroid 2012 DA14 made a close approach to Earth, passing within about 28,000 kilometers of the surface. The two events were unrelated, with the objects approaching from completely different directions. But the coincidence highlighted the frequency of near-Earth object encounters. The Chelyabinsk meteor was the largest object to enter Earth's atmosphere since the Tunguska event of 1908, and it spurred increased interest and investment in asteroid detection and planetary defense. These notable asteroids and near-Earth objects represent the diversity of the small body population in our solar system. From the dwarf planets Ceres to the tiny Chelyabinsk impactor, from metallic Psyche to carbonaceous Bennu, each asteroid tells its own story about the formation and evolution of our planetary system. As we continue to explore these ancient wanderers with spacecraft and telescopes, we gain ever deeper insights into our cosmic origins and the dynamic environment in which our planet exists. Throughout the history of our solar system, collisions between celestial bodies have shaped the worlds we see today. From the formation of the Moon to the extinction of the dinosaurs, impacts have played a crucial role in planetary evolution and the history of life on Earth. Let us explore the science of cosmic impacts, examining how these violent events occur, what effects they produce, and how they have influenced the course of Earth's history. The solar system is not a static, peaceful place, but rather a dynamic environment where objects occasionally collide with devastating consequences. Every day, Earth is bombarded by approximately 100 tons of material from space, mostly in the form of tiny dust particles that burn up harmlessly in the atmosphere as meteors. Larger objects strike less frequently, but with proportionally greater effects. Objects a few meters across enter the atmosphere several times per year, usually exploding at high altitude and causing no damage on the ground. Objects tens of meters across, like the Chelyabinsk impactor, strike every few decades to centuries and can cause significant local damage. Objects hundreds of meters across strike every few thousand to tens of thousands of years and could devastate a region or cause global climate effects. Objects a kilometer or larger strike every few 100,000 to millions of years and could cause mass extinctions. The relationship between impactor size and impact frequency follows a power law, meaning that small impacts are far more common than large ones. This relationship has been calibrated by studying the crater populations on the Moon and other bodies, by analysing the size distribution of near-Earth asteroids, and by examining the geological record of impacts on Earth. While the exact numbers are uncertain, the general pattern is clear. Catastrophic impacts are rare on human timescales, but inevitable on geological timescales. When an asteroid or comet strikes a planetary surface, the kinetic energy of the impactor is converted into other forms of energy with devastating efficiency. An object travelling at typical solar system velocities of 10 to 70 kilometers per second carries enormous kinetic energy, far more than the same mass of chemical explosives. A 1-kilometer asteroid striking Earth at 20 kilometers per second would release energy equivalent to approximately 100 million megatons of TNT, millions of times more powerful than the largest nuclear weapons ever built. This energy is released in a fraction of a second, producing effects that dwarf any natural disaster in human experience. The impact process begins when the impactor enters the atmosphere. Small objects are slowed and heated by atmospheric friction, often breaking apart or exploding before reaching the surface. The Chelyabinsk meteor exploded at an altitude of about 30 kilometers, and the Tunguska object in 1908 apparently exploded at an altitude of 5 to 10 kilometers, flattening 2,000 square kilometers of Siberian forest without creating a crater. Larger objects, however, are barely affected by the atmosphere and strike the surface at nearly their original velocity. When a large impactor strikes the surface, it penetrates into the ground while transferring its kinetic energy to the target material. The impactor and the surrounding rock are subjected to pressures millions of times greater than atmospheric pressure, far exceeding the strength of any material. Both the impactor and the target rock are vaporized, melted, or shattered, depending on their distance from the point of impact. A shockwave propagates outward through the ground, compressing and fracturing rock far beyond the immediate impact site. The crater formation process occurs in 3 stages. In the contact and compression stage, lasting only a fraction of a second, the impactor transfers its energy to the target. In the excavation stage, lasting seconds to minutes depending on the crater size, material is ejected from the growing cavity by the expanding shockwave. The transient crater formed during this stage is roughly hemispherical and much deeper than the final crater. In the modification stage, the unstable transient crater collapses under gravity, with the walls slumping inward and the floor rebounding upward. For large craters, this modification produces a central peak, or peak ring, formed as the compressed floor rebounds like a water droplet splashing upward after a stone is dropped into a pond. The final crater is much shallower than the transient crater, with a depth-to-diameter ratio of roughly 1 to 10 for simple craters and even shallower for complex craters with central peaks. The rim of the crater is raised above the surrounding terrain by material pushed up and outward during the excavation stage. A blanket of ejected material, called the ejector blanket, surrounds the crater, thickest near the rim and thinning with distance. Some ejector is thrown on ballistic trajectories that carry it hundreds or thousands of kilometers from the impact site, and for the largest impacts, material can be ejected at velocities exceeding Earth's escape velocity, sending fragments into orbit around the Sun or even to other planets. The Chicxulub impact, which occurred approximately 66 million years ago on what is now the Yucatan Peninsula of Mexico, is the most famous impact event in Earth's history due to its association with the extinction of the non-avian dinosaurs. The impactor was approximately 10 to 15 kilometers in diameter, either an asteroid or a comet, and struck the shallow sea that covered the region at that time. The impact created a crater approximately 180 kilometers in diameter and released energy equivalent to roughly 100 million megatons of TNT. The immediate effects of the Chicxulub impact were catastrophic. The impact generated enormous tsunamis that swept across the Gulf of Mexico and adjacent coastlines. Earthquakes far more powerful than any in recorded human history shook the entire planet. A fireball expanded outward from the impact site, incinerating everything within a radius of perhaps 1,000 kilometers. Molten rock ejected from the crater rained down across the Americas and beyond, potentially igniting wildfires on a continental scale. The longer-term effects were even more devastating for life on Earth. The impact injected vast quantities of dust and sulfur compounds into the atmosphere, blocking sunlight and causing global temperatures to plummet. Photosynthesis was severely reduced or halted entirely for months to years, collapsing food chains on land and in the oceans. Acid rain, produced when sulfur compounds combined with water in the atmosphere, may have acidified surface waters and damaged vegetation. The combination of these effects caused one of the 5 great mass extinctions in Earth's history, eliminating approximately 75% of all species, including all non-avian dinosaurs, pterosaurs, marine reptiles, and ammonites. The evidence for the Chicxulub impact and its role in the end Cretaceous extinction has accumulated over decades of research. In 1980, physicist Luis Alvarez and his geologist son Walter Alvarez discovered a thin layer of clay at the Cretaceous-Paleogene boundary that was highly enriched in iridium, an element rare in Earth's crust but common in asteroids. They proposed that this iridium layer was deposited by a large asteroid impact, and that the impact caused the mass extinction. The discovery of the Chicxulub crater in 1991, buried beneath younger sediments on the Yucatan Peninsula, provided the smoking gun that confirmed the impact hypothesis. The Chicxulub impact was not the only large impact in Earth's history, merely the most recent one associated with a mass extinction. The Vredefort crater in South Africa, approximately 2 billion years old and originally about 300 kilometers in diameter, is the largest confirmed impact structure on Earth. The Sudbury Basin in Ontario, Canada, formed about 1.85 billion years ago, is the second largest at approximately 250 kilometers in diameter. The Sudbury impact was so large that it may have triggered volcanic activity and influenced the evolution of early life. These ancient craters have been heavily eroded and modified by geological processes, but their impact origins can still be determined from the distinctive features they preserve. The Tunguska event of June 30, 1908 remains the largest impact event in recorded human history, though it left no crater. An object estimated at 50 to 80 meters in diameter exploded at an altitude of 5 to 10 kilometers above the Siberian taiga, releasing energy equivalent to roughly 10 to 15 megatons of TNT. The explosion flattened approximately 2,000 square kilometers of forest, knocking down an estimated 80 million trees. The blast wave was detected by barometers around the world, and the dust injected into the atmosphere produced unusually bright night skies across Europe for several days. The Tunguska object was probably a stony asteroid, or possibly a small comet that disintegrated under the stresses of atmospheric entry. The lack of a crater and the absence of significant meteorite fragments suggest that the object was completely destroyed in the explosion. If the Tunguska event had occurred over a populated area, the casualties would have been enormous. The event serves as a reminder that even relatively small objects can cause significant damage, and that such events occur on timescales relevant to human civilization. Meteor Crater in Arizona, also known as Barringer Crater, is the best preserved impact crater on Earth and has played a crucial role in the scientific understanding of impact processes. The crater is approximately 1.2 kilometers in diameter and 170 meters deep, formed about 50,000 years ago by an iron meteorite, roughly 50 meters in diameter. The impactor, travelling at approximately 12 kilometers per second, released energy equivalent to about 10 megatons of TNT. Much of the meteorite was vaporized or melted on impact, but fragments totaling about 30 tons have been recovered from the surrounding area. Meteor Crater was the first terrestrial feature to be definitively identified as an impact crater, though this recognition came only after decades of controversy. Mining engineer Daniel Barringer became convinced in 1903 that the crater was formed by a meteorite impact and spent years searching for the main mass of the meteorite, which he believed lay buried beneath the crater floor. Barringer never found the buried meteorite because most of it had been destroyed on impact, but his work helped establish the importance of impact cratering as a geological process. The Moon preserves a far more complete record of impact cratering than Earth because it lacks the atmosphere, water, and geological activity that erode and bury craters on our planet. The lunar surface is saturated with craters, from microscopic pits to enormous basins hundreds of kilometers across. The largest lunar impact basins, such as the South Pole Aitken Basin on the Moon's far side, are over 2,000 kilometers in diameter and represent some of the largest impact structures in the solar system. The lunar crater record has been used to calibrate the impact flux throughout solar system history. By dating lunar samples returned by the Apollo missions and correlating them with crater counts, scientists have established that the impact rate was much higher early in solar system history than it is today. The late heavy bombardment, a period of intense cratering approximately 4 billion years ago, may have been triggered by the migration of the giant planets, which destabilized populations of small bodies and sent them careening through the inner solar system. This bombardment would have had profound effects on the early Earth, potentially sterilizing the surface multiple times and delivering water and organic compounds from the outer solar system. Understanding impact hazards has become an important area of scientific research and public policy. Astronomers have conducted systematic surveys to discover and track near-Earth asteroids, with the goal of identifying any objects that might pose a threat to Earth. As of late 2024, over 35,000 near-Earth asteroids have been discovered, including more than 2,000 classified as potentially hazardous based on their size and orbital characteristics. No known asteroid currently poses a significant threat to Earth in the foreseeable future, but the surveys are not yet complete, and undiscovered objects could still pose a risk. Planetary defense strategies focus on two main approaches: deflection and disruption. Deflection involves changing an asteroid's orbit so that it misses Earth, while disruption involves breaking the asteroid into smaller pieces that either miss Earth or cause less damage individually. The DART mission's successful demonstration of kinetic impactor technology in 2022 showed that deflection is technically feasible, at least for smaller asteroids, with sufficient warning time. Other proposed deflection methods include gravity tractors, which would use a spacecraft's gravitational attraction to slowly alter an asteroid's orbit, and ion beam deflection, which would use a spacecraft's ion engine exhaust to push on an asteroid's surface. The key to planetary defense is early detection. An asteroid discovered decades before a potential impact could be deflected with relatively modest technology, while an asteroid discovered only months or years before impact would require much more aggressive intervention. Continued investment in asteroid surveys and tracking is therefore essential for protecting Earth from future impacts. The cosmic shooting gallery in which our planet exists has shaped the history of life on Earth and will continue to pose risks in the future. By understanding impact processes and developing the technology to detect and deflect threatening objects, we can hope to avoid the fate of the dinosaurs and ensure the long-term survival of our civilization. The exploration of asteroids and comets by spacecraft represents one of humanity's greatest scientific achievements. Over the past several decades, we have sent robotic emissaries to fly past, orbit, land upon, and even return samples from these ancient wanderers. Each mission has revealed new wonders and deepened our understanding of the small bodies that populate our solar system. Let us trace the history of these remarkable expeditions and celebrate the ingenuity and determination that made them possible. The first spacecraft to visit an asteroid was NASA's Galileo, which flew past the asteroid Gaspra in October 1991 while en route to Jupiter. Gaspra, an S-type asteroid with dimensions of approximately 19 by 12 by 11 kilometers, was revealed to be an irregularly shaped body covered in small craters and grooves. The images returned by Galileo, taken from a distance of about 1,600 kilometers, showed that Gaspra's surface was relatively young, with fewer large craters than expected, suggesting that the asteroid might be a fragment from a larger body that was disrupted relatively recently, in geological terms, perhaps 300 to 500 million years ago. 2 years later, in August 1993, Galileo flew past the asteroid Ida and discovered its tiny moon Dactyl, the first asteroid moon ever observed. NASA's Near-Shoemaker mission, launched in 1996, was the first spacecraft dedicated to asteroid exploration. After a flyby of the asteroid Matilde in June 1997, Near-Shoemaker entered orbit around the asteroid Eros in February 2000, becoming the first spacecraft to orbit an asteroid. For an entire year, the spacecraft circled this elongated, potato-shaped world, mapping its surface in exquisite detail and measuring its gravity field, composition, and internal structure. Eros proved to be a consolidated body, approximately 34 kilometers long, covered in craters, boulders, and a layer of fine regolith. The spacecraft discovered that Eros has a relatively uniform interior, unlike the rubble pile structure found in some other asteroids. In February 2001, Near-Shoemaker concluded its mission with an audacious maneuver that was never part of the original plan. Controllers guided the spacecraft to a gentle touchdown on the surface of Eros, making it the first spacecraft to land on an asteroid. Although Near-Shoemaker was not designed as a lander and had no landing legs, it survived the touchdown and continued transmitting data from the surface for about 2 weeks. The gamma-ray spectrometer collected valuable compositional data during this surface phase, providing information about the elemental abundances in the asteroid's regolith. This unexpected bonus demonstrated the value of flexibility and creativity in space exploration. Japan's Hayabusa mission, launched in 2003, attempted something even more ambitious, collecting samples from an asteroid and returning them to Earth. The target was Itokawa, a small near-Earth asteroid approximately 535 meters long with a distinctive peanut shape. Hayabusa arrived at Itokawa in September 2005 and spent several months studying the asteroid from close range. The spacecraft revealed that Itokawa is a rubble pile asteroid, a loose aggregate of boulders and smaller fragments held together by weak gravity rather than material strength. The surface showed 2 distinct terrains, rough boulder-strewn highlands and smooth gravel-filled lowlands. The sample collection attempts in November 2005 were plagued by technical difficulties. The spacecraft was designed to fire a small projectile into the surface and collect the debris stirred up by the impact, but the projectile failed to fire during both touchdown attempts. Nevertheless, the spacecraft did briefly touch the surface, and scientists hoped that some particles might have been stirred up and entered the collection chamber. After a harrowing journey home that included the failure of 2 reaction wheels, a fuel leak, and the loss of the primary ion engine, Hayabusa returned its sample capsule to Earth in June 2010. When scientists opened the capsule, they found approximately 1,500 tiny grains of asteroidal material, enough to confirm that sample return from an asteroid was possible and to provide valuable scientific data about Itokawa's composition. The European Space Agency's Rosetta mission, launched in 2004, was one of the most ambitious comet exploration missions ever attempted. The spacecraft's goal was to rendezvous with Comet 67 pair Churyumov-Gerasimenko, accompany it as it approached the Sun, and deploy a lander to the comet's surface. To reach its target, Rosetta performed a complex series of gravity assist maneuvers, flying past Earth 3 times and Mars once over a period of 10 years. Along the way, Rosetta flew past 2 asteroids, Steins in 2008 and Lutetia in 2010, providing bonus science and testing the spacecraft's instruments. Rosetta arrived at Comet 67P in August 2014, becoming the first spacecraft to orbit a comet. The comet's nucleus proved to be a remarkable object, shaped like a rubber duck, with 2 distinct lobes connected by a narrow neck. This unusual shape may have formed when 2 separate bodies gently collided and merged billions of years ago, or it may have resulted from erosion that preferentially removed material from the neck region. The nucleus measured approximately 4.3 by 4.1 kilometers, with a rotation period of about 12.4 hours. Over the following 2 years, Rosetta accompanied Comet 67P as it approached the Sun, reached perihelion in August 2015, and then retreated back toward the outer solar system. The spacecraft observed the comet's activity increase dramatically as solar heating intensified, with jets of gas and dust erupting from active regions on the surface. Rosetta's instruments detected dozens of different molecules in the comet's coma, including water, carbon dioxide, carbon monoxide, and complex organic compounds. The spacecraft also discovered molecular oxygen in the coma, an unexpected finding that suggested the oxygen had been incorporated into the comet's ice when it formed in the early solar system. In November 2014, Rosetta deployed its Philae lander for the first attempted landing on a comet. The landing did not go as planned. Philae's harpoons, designed to anchor it to the surface, failed to fire, and the lander bounced twice before coming to rest in a shadowed location near a cliff. The final landing site received much less sunlight than intended, limiting the lander's ability to recharge its batteries. Philae operated for about 60 hours on its primary battery, collecting valuable data about the comet's surface composition and properties before entering hibernation. The lander briefly reawakened in June and July 2015 as the comet approached the Sun, and more light reached its solar panels, but communication was intermittent and limited. Despite the landing difficulties, Philae returned groundbreaking science. The lander detected 16 organic compounds in the cometary material, including 4 that had never before been found on a comet. The surface proved to be harder than expected, with a thin layer of dust overlying a more consolidated substrate. Philae's measurements of the comet's magnetic field showed that the nucleus has no global magnetic field, an important constraint on theories of how comets and planetesimals formed in the early solar system. Rosetta concluded its mission in September 2016 with a controlled descent to the comet's surface. As the spacecraft slowly approached the nucleus, it returned increasingly detailed images of the surface, revealing features as small as a few centimeters across. The final image, transmitted just before impact, showed a patch of surface from an altitude of about 20 meters. Rosetta's impact ended one of the most successful and scientifically productive missions in the history of space exploration. NASA's Deep Impact mission, launched in January 2005, took a more dramatic approach to comet exploration. The spacecraft carried an impactor designed to crash into Comet Tempel 1 and excavate material from beneath the surface, allowing the flyby spacecraft to study the composition of the comet's interior. On July 4, 2005, the impactor separated from the main spacecraft and guided itself to a collision with the comet's nucleus at a relative velocity of about 10 kilometers per second. The impact released energy equivalent to about 4.8 tons of TNT and excavated a crater estimated at 100 to 250 meters in diameter. The flyby spacecraft observed the impact from a safe distance, capturing images and spectra of the ejector plume. The impact released far more dust than expected, creating a cloud so thick that the spacecraft could not see the crater itself. Analysis of the ejector revealed that Comet Tempel 1 contains water ice, organic compounds, and silicate minerals, with a composition similar to other comets that have been studied. The comet's interior appeared to be more dusty and less icy than the surface, suggesting that solar heating had modified the outer layers over many perihelion passages. After its primary mission, Deep Impact was repurposed for an extended mission called Epoxy, which combined two objectives: observing extrasolar planet transits and flying past another comet. In November 2010, the spacecraft flew past Comet Hartley 2, providing detailed images of a small active comet nucleus. Hartley 2 proved to be a peanut-shaped body, about 2.2 kilometers long, with jets of carbon dioxide gas erupting from the ends and water vapor sublimating from the smooth middle section. The spacecraft observed chunks of ice being ejected from the nucleus, some as large as basketballs, providing direct evidence of the process by which comets lose mass. NASA's Stardust mission, launched in 1999, achieved another historic first, returning samples from a comet to Earth. The spacecraft flew through the coma of Comet Wild 2 in January 2004, using a collector filled with aerogel, an extremely low-density material that could capture high-speed particles without destroying them. The aerogel collector was exposed to the comet's coma for about 5 minutes, during which thousands of particles became embedded in the material. Stardust also captured interstellar dust particles during its cruise through the solar system, providing samples of material from beyond our planetary system. The sample return capsule landed in the Utah desert in January 2006, and scientists eagerly began analyzing the precious cometary material. The samples revealed that Comet Wild 2 contains a surprising mixture of materials formed at both high and low temperatures. Some particles were rich in the mineral olivine, which forms at temperatures above 1000 degrees Celsius, while others contained water-bearing minerals and organic compounds that could only have formed at much lower temperatures. This mixture suggests that material was transported across vast distances in the early solar nebula, from the hot inner regions near the young sun to the cold outer regions where comets formed. The Stardust samples also contain the amino acid glycine, the simplest amino acid and a building block of proteins. This discovery supported the hypothesis that comets may have delivered some of the organic molecules necessary for life to the early Earth. The samples continue to be studied today, with new analytical techniques revealing ever more details about the composition and history of cometary material. Japan's Hayabusa 2 mission, launched in December 2014, built on the experience gained from the original Hayabusa mission to achieve a more complete and successful asteroid sample return. The target was Ryugu, a carbonaceous near-Earth asteroid approximately 900 meters in diameter. Hayabusa 2 arrived at Ryugu in June 2018 and spent the next year and a half studying the asteroid in unprecedented detail. Ryugu proved to be a rubble pile asteroid with a distinctive spinning top shape, featuring a prominent equatorial ridge that gives it a diamond-like profile when viewed from the side. The surface was rougher than expected, covered in boulders with very little fine-grained material. This boulder-strewn terrain complicated the sample collection process, as the spacecraft needed to find a relatively smooth area to touch down safely. Hayabusa 2 deployed several small rovers to Ryugu's surface, including 2 Minerva 2 rovers and the German-French mascot lander. The Minerva 2 rovers were the first mobile robots to operate on an asteroid surface, hopping across the low-gravity terrain by spinning internal flywheels. Mascot operated for about 17 hours, studying the surface composition and properties at multiple locations before its battery was exhausted. The spacecraft collected samples from 2 locations on Ryugu. The first sample was collected in February 2019 from the asteroid's surface. The second sample was collected in July 2019 from a site where Hayabusa 2 had previously created an artificial crater using a kinetic impactor. This second sample included material excavated from beneath the surface, providing access to material that had been shielded from space weathering and solar radiation. Hayabusa 2 departed Ryugu in November 2019 and returned its sample capsule to Earth in December 2020, landing in the Australian outback. The capsule contained approximately 5.4 grams of asteroidal material, far exceeding the mission's minimum goal of 0.1 grams. Analysis of the Ryugu samples has revealed that the asteroid contains some of the most primitive material ever studied, with a composition similar to the Sun and containing water, organic compounds, and pre-solar grains that formed before our solar system existed. The samples include amino acids and other organic molecules that may have played a role in the origin of life on Earth. NASA's OSIRIS-REx mission, launched in September 2016, targeted another carbonaceous near-Earth asteroid, Bennu. The spacecraft arrived at Bennu in December 2018 and spent nearly 2 years mapping the asteroid's surface and selecting a sample collection site. Like Ryugu, Bennu proved to be a rubble-pile asteroid with a rough, boulder-strewn surface that complicated sample collection planning. Bennu is approximately 500 meters in diameter, with a spinning top shape similar to Ryugu. The asteroid rotates once every 4.3 hours and is gradually spinning faster over time due to the Oort effect, a phenomenon in which uneven heating and cooling of an asteroid's surface creates a tiny torque that changes its rotation rate. Scientists estimate that Bennu's rotation rate will continue to increase until the asteroid eventually flies apart, perhaps in 1 million years or so. The sample collection event occurred in October 2020 at a site named Nightingale, a relatively smooth area within a crater near Bennu's north pole. The spacecraft descended to the surface and extended its collection arm, which touched the asteroid for approximately 6 seconds while firing a burst of nitrogen gas to stir up loose material. The collection was so successful that the sample container was overfilled, and some material was escaping through gaps in the lid. Controllers quickly stowed the sample container to prevent further loss. OSIRIS-REx departed Bennu in May 2021 and returned its sample capsule to Earth in September 2023, landing in the Utah desert. The capsule contained approximately 121 grams of asteroidal material, far exceeding the mission's goal of 60 grams. Preliminary analysis has revealed that the Bennu samples contain abundant water-bearing minerals, carbon compounds, and organic molecules, including amino acids. The samples will be studied for decades to come, providing insights into the early solar system and the potential role of asteroids in delivering the ingredients for life to Earth. NASA's Dawn mission, launched in September 2007, was the first spacecraft to orbit 2 different extraterrestrial bodies. Using ion propulsion, which provides gentle but continuous thrust over long periods, Dawn was able to enter orbit around the asteroid Vesta in July 2011, study it for over a year, and then depart and travel to the dwarf planet Ceres. arriving in March 2015. At Vesta, Dawn revealed a world that had experienced significant geological evolution. The asteroid has a differentiated interior with an iron core, rocky mantle, and basaltic crust, more similar in structure to the terrestrial planets than to most asteroids. The massive Rhea Silvia impact basin near the South Pole, approximately 505 kilometers in diameter, dominates the asteroid's southern hemisphere. This impact excavated material from deep within Vesta, and fragments ejected by the impact have made their way to Earth as the head meteorites, giving us samples of Vesta without the need for a sample return mission. At Ceres, Dawn discovered a world of unexpected complexity. The dwarf planet's surface displays a variety of geological features, including impact craters, mountains, and mysterious bright spots that puzzled scientists when first observed from a distance. These bright spots, concentrated in the crater Achater, proved to be deposits of sodium carbonate, a type of salt that suggests briny water has reached the surface from a subsurface reservoir. The mountain Ahuna Mons appears to be a cryovolcano, a volcano that erupts water and other volatiles rather than molten rock. Ceres may harbour a subsurface ocean of liquid water, making it a potential target for future astrobiological exploration. Dawn exhausted its hydrazine fuel in late 2018 and remains in orbit around Ceres, where it will stay for at least several decades. The spacecraft's discoveries have transformed our understanding of the largest objects in the asteroid belt and demonstrated the power of ion propulsion for exploring multiple targets in a single mission. NASA's Lucy mission, launched in October 2021, is currently on a 12-year journey to explore the Trojan asteroids, populations of small bodies that share Jupiter's orbit, clustered around point 60 degrees ahead of and behind the giant planet. These Trojan asteroids are thought to be primitive objects captured from the outer solar system during the early history of planetary migration, making them valuable targets for understanding solar system formation. Lucy will fly past a total of 8 asteroids during its mission, 1 main belt asteroid and 7 Trojans. The first flyby occurred in November 2023 when Lucy passed the small main belt asteroid Dinkinesh and discovered that it has a tiny contact binary moon, making the system a triple asteroid. Lucy will reach the first Trojan targets in 2027 and continue its tour through 2033, providing the first close-up views of these distant and mysterious objects. NASA's Psyche mission, launched in October 2023, is en route to the metallic asteroid Psyche, one of the most intriguing objects in the asteroid belt. Psyche appears to be composed primarily of iron and nickel, possibly representing the exposed core of a protoplanet that was stripped of its rocky mantle by violent collisions early in solar system history. The spacecraft will arrive at Psyche in 2029 and spend approximately 2 years orbiting the asteroid, mapping its surface, measuring its gravity field, and determining its composition. If Psyche is indeed a planetary core, it will provide unique insights into the interiors of terrestrial planets like Earth. The European Space Agency's Hera mission, launched in October 2024, is travelling to the Didymos Dimorphos binary asteroid system to conduct a detailed investigation of the aftermath of NASA's DART impact. DART successfully changed the orbit of Dimorphos in September 2022, demonstrating that kinetic impact or technology can deflect an asteroid. Hera will arrive in late 2026 and study the impact crater, measure the mass of Dimorphos, and characterize how the impact affected the asteroid's structure and orbit. This follow-up investigation will provide crucial information for refining planetary defense strategies. These missions represent humanity's growing capability to explore and understand the small bodies of our solar system. From the first tentative flybys to sophisticated sample return missions, each expedition has revealed new wonders and deepened our appreciation for the diversity and complexity of asteroids and comets. As we continue to send spacecraft to these ancient wanderers, we are not merely satisfying scientific curiosity, but also preparing to protect our planet from potential impacts, and perhaps one day to utilize the resources these bodies contain. Understanding the composition of asteroids and comets is essential for unraveling the history of our solar system and assessing both the hazards and opportunities these objects present. The materials that make up these ancient bodies preserve information about conditions in the solar nebula 4.6 billion years ago, information that has been erased on larger planets by geological activity. Let us explore what asteroids and comets are made of and how scientists have determined their compositions. Asteroids display a remarkable diversity of compositions, reflecting the different conditions under which they formed and the various processes that have modified them over billions of years. The classification of asteroids by composition began with spectroscopic observations, which analysed the light reflected from asteroid surfaces at different wavelengths. Different minerals reflect light in characteristic ways, allowing astronomers to infer surface composition from the spectral signature. The most common asteroid types are designated by letters that originally stood for descriptive terms. C-type asteroids, where C stands for carbonaceous, are dark objects that reflect only about 3 to 4% of the sunlight that falls on them. These asteroids are rich in carbon compounds and often contain water bound within hydrated minerals. C-type asteroids are most common in the outer regions of the asteroid belt, where temperatures were low enough during solar system formation for volatile compounds to be retained. The asteroid Bennu, from which OSIRIS-REx returned samples, is a C-type asteroid, and analysis of those samples has confirmed the presence of water-bearing minerals, organic compounds, and amino acids. S-type asteroids, where S stands for silicaceous or stony, are brighter than C-types and are composed primarily of silicate minerals like olivine and pyroxene, along with metallic iron and nickel. These asteroids dominate the inner regions of the asteroid belt, where higher temperatures during solar system formation drove off volatile compounds. S-type asteroids are thought to be the parent bodies of ordinary chondrite meteorites, the most common type of meteorite to fall on Earth. The asteroid Itokawa, from which Hayabusa returned samples, is an S-type asteroid. M-type asteroids, where M stands for metallic, appear to be composed primarily of iron and nickel. These asteroids may be the exposed cores of larger bodies that differentiated early in solar system history, with heavy metals sinking to the centre while lighter rocky material floated to the surface. Subsequent collisions shattered these differentiated bodies, exposing their metallic cores. The asteroid Psyche is the largest known M-type asteroid and is the target of an ongoing NASA mission. Beyond these three main types, dozens of additional spectral classes have been defined to capture the full diversity of asteroid compositions. V-type asteroids have surfaces rich in the mineral pyroxene and are associated with the asteroid Vesta, which has a basaltic crust formed by ancient volcanic activity. D-type and P-type asteroids are very dark objects found primarily in the outer asteroid belt and among the Trojan asteroids, with compositions that may include organic compounds and water ice. E-type asteroids have very bright surfaces composed of the mineral enstatite, a magnesium silicate that forms under highly reducing conditions. The composition of an asteroid's interior may differ from its surface composition due to a process called space weathering. Exposure to solar radiation, cosmic rays, and micrometeorite impacts gradually alters the optical properties of asteroid surfaces, darkening them and changing their spectral signatures. This weathering can make it difficult to determine the true composition of an asteroid from remote observations alone. Sample return missions like Hayabusa, Hayabusa 2, and OSIRIS-REx have provided ground truth by returning actual asteroid material for laboratory analysis, allowing scientists to calibrate their remote sensing techniques. Meteorites provide another window into asteroid composition. These fragments of asteroids that have fallen to Earth can be analysed in detail using laboratory techniques far more sensitive than any spacecraft instrument. The thousands of meteorites in scientific collections represent a diverse sampling of asteroid compositions, though the sample is biased towards stronger materials that can survive the passage through Earth's atmosphere. Chondrite meteorites are the most primitive type, composed of material that has changed little since the solar system formed. They contain small spherical structures called chondrules, which are droplets of silicate material that melted and then rapidly cooled in the solar nebula before being incorporated into larger bodies. Chondrules are found only in meteorites and have no counterpart in terrestrial rocks, making them unique windows into conditions in the early solar system. Carbonaceous chondrites are a subtype that contains significant amounts of carbon compounds and water-bearing minerals, similar to the material found in C-type asteroids and in the samples returned from Bennu and Ryugu. Achondrite meteorites are igneous rocks that formed when their parent bodies melted and differentiated. These meteorites lack chondrules because the melting process destroyed any that were originally present. Achondrites include basaltic rocks from the crust of differentiated asteroids, as well as samples from the Moon and Mars that were ejected by impacts and eventually fell to Earth. The Hades meteorites, believed to originate from Vesta, are achondrites that provide samples of that asteroid's basaltic crust. Iron meteorites are composed almost entirely of iron and nickel, representing the cores of differentiated asteroids that were shattered by collisions. When cut and polished, iron meteorites often display a distinctive pattern called Widmanstetten figures, interlocking bands of two different iron-nickel alloys that formed as the metal cooled extremely slowly over millions of years. This slow cooling could only have occurred deep within a large body, confirming that iron meteorites come from the cores of objects at least tens of kilometers in diameter. Stony iron meteorites contain roughly equal amounts of silicate rock and metallic iron nickel, representing material from the boundary between the core and mantle of differentiated asteroids. Pallasites, the most beautiful type of stony iron meteorite, contain crystals of the green mineral olivine embedded in a matrix of metallic iron nickel. When sliced thin and backlit, pallasites display stunning patterns of translucent green crystals surrounded by gleaming metal. Comets have a fundamentally different composition from asteroids, reflecting their formation in the cold outer regions of the solar nebula. The primary component of comet nuclei is water ice, which makes up roughly 40 to 80% of the mass depending on the individual comet. But cometary ice is not pure water. It contains a complex mixture of other frozen volatile compounds, including carbon dioxide, carbon monoxide, methane, ammonia, hydrogen sulfide, and formaldehyde. These ices are intimately mixed with dust particles composed of silicate minerals and organic compounds. The organic compounds in comets are particularly interesting because they may have contributed to the origin of life on Earth. Spectroscopic observations of cometary coma have detected dozens of different organic molecules, from simple compounds like methane and methanol to more complex species like ethylene glycol and glycine, the simplest amino acid. The Rosetta mission detected 16 organic compounds on the surface of Comet 67P, including several that had never before been found on a comet. The Stardust mission returned samples containing glycine and other organic molecules, confirming that comets carry the chemical building blocks of life. The dust in comets includes both crystalline and amorphous silicate minerals. Crystalline silicates, particularly olivine and pyroxene, form at high temperatures and were originally thought to be absent from comets, which formed in the cold outer solar system. The discovery of crystalline silicates in cometary dust by the Stardust mission was therefore surprising and suggests that material was transported across vast distances in the early solar nebula, from the hot inner regions near the young sun to the cold outer regions where comets formed. Comets also contain presolar grains, tiny particles that formed in the atmospheres of dying stars before our solar system existed. These grains have isotopic compositions that differ from solar system material, allowing them to be identified and studied individually. Presolar grains in comets include diamond, silicon carbide, graphite, and various oxides, each type originating from different stellar environments. The presence of presolar grains in comets confirms that these objects preserve material from before the birth of our solar system, making them true time capsules from the distant past. The density of comet nuclei is surprisingly low, typically about 0.4 to 0.6 grams per cubic centimetre, less than the density of water ice. This low density indicates that comet nuclei are highly porous, with significant void space between the ice and dust particles. Some estimates suggest that comet nuclei may be as much as 70 to 80% empty space, making them extremely fragile structures. This porosity likely results from the gentle accumulation of small icy particles in the outer solar system, which stuck together without being compressed into a solid mass. The ratio of deuterium to hydrogen in cometary water provides clues to the origin of Earth's oceans. Deuterium is a heavy isotope of hydrogen, and the deuterium to hydrogen ratio varies depending on the temperature and conditions under which water formed. Measurements of this ratio in several comets have shown considerable variation. Some comets, particularly those from the Kuiper Belt, have deuterium to hydrogen ratios similar to Earth's oceans, suggesting that cometary impacts could have contributed to Earth's water supply. Other comets, particularly those from the Oort Cloud, have much higher ratios, indicating they formed under different conditions. The composition of asteroids and comets is not merely of academic interest. Understanding what these objects are made of is essential for planetary defense, as the response to a potential impactor depends on whether it is a solid rock, a rubble pile, or an icy body. Composition also matters for future resource utilization, as asteroids contain valuable metals and water that could potentially be extracted and used to support space exploration. The water in carbonaceous asteroids and comets could be converted to rocket fuel, while metallic asteroids contain iron, nickel, and precious metals in quantities that dwarf terrestrial reserves. As we continue to study the composition of asteroids and comets through remote sensing, spacecraft missions, and sample return, we are building an ever more detailed picture of the materials that make up our solar system. These ancient bodies are not merely rocks and ice, but complex assemblages of minerals, organic compounds, and pre-solar grains that preserve information about the birth of our planetary system and perhaps the origin of life itself. As we look toward the future, asteroids and comets are poised to play increasingly important roles in human civilization. These ancient bodies offer resources that could support the expansion of humanity into space, pose hazards that we must learn to mitigate, and present scientific opportunities that will deepen our understanding of the cosmos. Let us explore what the coming decades may bring as we continue to reach out to these wanderers of the solar system. The concept of asteroid mining has captured the imagination of entrepreneurs, engineers, and space agencies around the world. Asteroids contain vast quantities of valuable materials, including water, metals, and rare elements that are scarce on Earth. A single metallic asteroid a kilometre in diameter could contain more iron, nickel, and cobalt than has been mined in all of human history. The platinum group metals, which are rare and expensive on Earth, are relatively abundant in certain types of asteroids. Water, perhaps the most valuable resource for space operations, is present in carbonaceous asteroids and could be extracted and used to produce rocket fuel, drinking water, and oxygen for life support. The economics of asteroid mining are challenging but potentially transformative. The high cost of launching material from Earth's surface means that resources already in space have enormous value for supporting space operations. Water, extracted from an asteroid and converted to hydrogen and oxygen propellant, could refuel spacecraft in orbit, dramatically reducing the cost of missions to the Moon, Mars, and beyond. Metals refined from asteroids could be used to construct space stations, habitats, and spacecraft without the expense of lifting those materials from Earth. Several companies have been founded to pursue asteroid mining, though the industry remains in its early stages. The technical challenges are formidable, including identifying suitable target asteroids, developing extraction and processing technologies that work in microgravity, and creating the infrastructure to transport materials to where they are needed. Legal and regulatory frameworks for space resource utilization are still being developed, with the United States, Luxembourg, and other nations passing laws that recognize the right of private entities to own resources extracted from asteroids. NASA's OSIRIS-REx and Japan's Hayabusa 2 missions have demonstrated that it is possible to collect material from asteroids and return it to Earth, though on a much smaller scale than would be needed for commercial mining. Future missions may test extraction technologies and assess the feasibility of processing asteroid materials in space. The knowledge gained from scientific missions is directly applicable to resource utilization, as understanding asteroid composition and structure is essential for designing effective mining systems. Planetary defense against asteroid and comet impacts has become an increasingly important area of research and international cooperation. The recognition that impacts pose a genuine threat to human civilization has spurred efforts to detect potentially hazardous objects, characterize their properties, and develop technologies to deflect or disrupt them if necessary. Asteroid surveys have made tremendous progress in cataloguing the near-Earth object population. As of late 2024, over 35,000 near-Earth asteroids have been discovered, including more than 2,000 classified as potentially hazardous based on their size and orbital characteristics. The surveys have found the vast majority of near-Earth asteroids larger than 1 kilometre in diameter, the size threshold above which an impact could cause global catastrophe. No known asteroid of this size poses a threat to Earth in the foreseeable future. However, the surveys are far less complete for smaller objects. Asteroids in the 100 to 300 metre size range, which could devastate a region or cause significant climate effects, are much more numerous and harder to detect. The Chelyabinsk impactor, only about 20 metres in diameter, was not detected before it entered Earth's atmosphere. Continued investment in survey capabilities is essential for providing the early warning needed to respond to potential threats. The DART mission's successful demonstration of kinetic impactor technology in 2022 marked a major milestone in planetary defense. By crashing into the asteroid Dimorphos and measurably changing its orbit, DART proved that we have the capability to deflect at least some asteroids, given sufficient warning time. The HERA mission's follow-up investigation will provide detailed information about the impact's effects, helping to refine models of how asteroids respond to kinetic impactors. Other deflection technologies are being studied for situations where kinetic impactors might not be sufficient. Gravity tractors would use a spacecraft's gravitational attraction to slowly alter an asteroid's orbit over years or decades, a gentle approach suitable for situations with long warning times. Ion beam deflection would use a spacecraft's ion engine exhaust to push on an asteroid's surface, providing continuous thrust without physical contact. Nuclear explosive devices, while controversial, might be necessary for large asteroids discovered with short warning times, either to deflect the asteroid through the momentum imparted by the explosion or to disrupt it into smaller fragments. International coordination is essential for planetary defense, as an asteroid impact is a global threat that requires a global response. The United Nations has established the International Asteroid Warning Network and the Space Mission Planning Advisory Group to coordinate detection efforts and response planning. These organizations bring together space agencies, astronomers, and emergency management officials from around the world to share information and develop response strategies. Scientific exploration of asteroids and comets will continue to expand in the coming decades, with missions planned or proposed to a wide variety of targets. NASA's Lucy mission is currently touring the Trojan asteroids, providing the first close-up views of these primitive objects that share Jupiter's orbit. The Psyche mission will arrive at its metallic target in 2029, potentially revealing the exposed core of a protoplanet. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, will wait at the Sun-Earth Lagrange point for a suitable long-period comet or interstellar object to approach, then race out to intercept it and provide the first close-up observations of a pristine comet from the Oort Cloud. Sample return missions have proven their value and will likely continue. China's Tianwen-2 mission, planned for launch around 2025, will collect samples from a near-Earth asteroid and return them to Earth. Future missions may attempt to return larger samples or to collect material from more challenging targets, such as active comets or metallic asteroids. Human exploration of asteroids remains a possibility for the more distant future. NASA's Artemis program is focused on returning humans to the Moon, but asteroids have been considered as potential destinations for crewed missions. The relatively low gravity of asteroids would make landing and surface operations very different from lunar or planetary exploration. Astronauts would not walk on an asteroid surface, but rather float beside it, anchoring themselves with tethers or handholds while collecting samples and conducting experiments. The experience would be more akin to spacewalking than to exploring a planetary surface. Near-Earth asteroids offer certain advantages as destinations for human exploration. Some pass close enough to Earth that travel times would be measured in weeks, rather than the months required to reach Mars. The delta V, or velocity change, needed to reach certain near-Earth asteroids is actually less than that required to land on the Moon, though the mission duration would be longer. A crewed asteroid mission could serve as a stepping stone between lunar exploration and Mars expeditions, testing deep space systems and operational procedures in a challenging but achievable environment. The scientific value of human asteroid exploration would be substantial. Astronauts could select samples with geological context, choosing specific rocks based on their appearance and location, rather than relying on the limited mobility of robotic systems. They could deploy instruments, conduct experiments, and respond to unexpected discoveries in ways that robots cannot. The presence of humans would also enable real-time decision-making without the communication delays that complicate robotic operations at distant targets. Several asteroid mission concepts have been studied over the years. NASA's now cancelled asteroid redirect mission would have sent a robotic spacecraft to collect a boulder from an asteroid and bring it to lunar orbit, where astronauts could visit and study it. While this specific mission was not pursued, the technologies developed for it continue to inform planning for future asteroid exploration. Private companies have also expressed interest in human asteroid missions, though such endeavours remain years or decades away. The discovery of interstellar objects passing through our solar system has opened an entirely new frontier for exploration. The detection of One-Eye Oumuamua in 2017 and Two-Eye Borisov in 2019 demonstrated that objects from other star systems occasionally pass through our cosmic neighbourhood. These interstellar visitors offer unprecedented opportunities to study material from other planetary systems without travelling to those systems ourselves. Intercepting an interstellar object would be extremely challenging due to their high velocities and unpredictable arrival times. By the time an interstellar object is discovered, it is typically already on its way out of the solar system, leaving little time to mount a mission. The European Space Agency's Comet Interceptor mission addresses this challenge by launching in advance and waiting at a stable point in space until a suitable target is identified. When a long-period comet or interstellar object is discovered on an inbound trajectory, Comet Interceptor will race out to meet it, providing close-up observations of an object making its first visit to the inner solar system. More ambitious concepts for interstellar object missions have been proposed, including spacecraft that would use advanced propulsion systems to catch up with departing objects. Such missions would require significant technological advances, but could return samples of material from another star system, one of the most profound scientific achievements imaginable. The study of asteroids and comets also informs our understanding of planetary formation around other stars. Debris disks observed around young stars are analogous to the asteroid belts and Kuiper belts in our own solar system, representing leftover material from planet formation. By studying the small bodies in our solar system, we gain insights into the processes that shape planetary systems throughout the galaxy. Exocomets, comets orbiting other stars, have been detected through the subtle dimming they cause when they pass in front of their host stars. The star Beta Pictoris, surrounded by a prominent debris disk, shows evidence of numerous exocomets falling toward the star, evaporating and producing tails as they approach. These observations confirm that comets are common features of planetary systems, and that the processes we observe in our solar system occur throughout the cosmos. The future of asteroid and comet science is bright with possibility. New telescopes, both ground-based and space-based, will discover thousands of additional objects and characterize their properties in unprecedented detail. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct a comprehensive survey of the southern sky that is expected to discover millions of asteroids and thousands of comets over its 10-year primary mission. The Near-Earth Object Surveyor mission, a space-based infrared telescope planned for launch in the late 2020s, will specifically target the detection of potentially hazardous asteroids, particularly those approaching from directions where ground-based telescopes have difficulty observing. Advanced propulsion technologies will enable missions to more distant and challenging targets. Solar electric propulsion, which uses sunlight to generate electricity that accelerates ionized propellant, has already demonstrated its value on missions like Dawn and is being used on the Psyche mission. Future developments in electric propulsion could enable faster travel times and more ambitious mission profiles. Solar sails, which use the pressure of sunlight for propulsion, offer the possibility of missions that require no propellant at all, potentially enabling long-duration exploration of the outer solar system. The miniaturization of spacecraft technology is opening new possibilities for asteroid and comet exploration. CubeSats and other small satellites can be built and launched at a fraction of the cost of traditional spacecraft, enabling more frequent missions and greater willingness to accept risk. The DART mission carried a small Italian CubeSat called LishaCube that separated before impact and photographed the collision and its aftermath. Future missions may deploy swarms of small spacecraft to study multiple targets or to provide different viewing angles of a single object. Artificial intelligence and machine learning are transforming how we discover and study asteroids and comets. Automated systems can sift through vast amounts of survey data to identify moving objects, classify them by type, and flag potentially hazardous objects for follow-up observation. Machine learning algorithms can analyze spacecraft images to identify geological features and select sampling sites. As these technologies continue to advance, they will enable more efficient use of telescope time and spacecraft resources. The integration of asteroid and comet science with broader questions about the origin of life represents one of the most exciting frontiers in planetary science. The discovery of amino acids, sugars, and other organic molecules in meteorites, cometary samples, and asteroid samples supports the hypothesis that impacts delivered some of the chemical building blocks necessary for life to the early Earth. Understanding the inventory of organic compounds in asteroids and comets and how those compounds are modified by radiation and heating is essential for assessing the role of cosmic delivery in the origin of life. Some researchers have proposed that life itself might have originated in space, in the warm, wet interiors of asteroids or comets, before being delivered to Earth by impacts. While this hypothesis remains speculative, the discovery of liquid water environments inside some asteroids and the presence of complex organic chemistry in cometary material make it worthy of serious consideration. Future missions that can search for biosignatures in asteroid or comet samples would address this profound question directly. The coming decades will see humanity's relationship with asteroids and comets evolve from one of passive observation to active engagement. We will continue to discover and catalogue these objects, characterize their properties, and visit them with spacecraft. We will develop the technologies to deflect potentially hazardous objects and protect our planet from impacts. We may begin to extract resources from asteroids to support space exploration and eventually human settlement beyond Earth. And we will continue to study these ancient wanderers for the insights they provide into the origin and evolution of our solar system and the emergence of life. As we contemplate this future, we can appreciate that asteroids and comets are not merely objects of scientific curiosity, but integral parts of our cosmic story. They are remnants of the building blocks from which our planet formed, carriers of water and organic molecules that may have seeded life on Earth, potential hazards that have shaped the history of life through catastrophic impacts, and resources that may enable humanity's future among the stars. Our growing understanding of these objects reflects our broader quest to understand our place in the universe and to ensure the long-term survival and flourishing of our species. As we reach the end of our journey through the story of asteroids and comets, let us take a moment to reflect on all that we have explored together. We began by considering how ancient peoples first observed these celestial wanderers, interpreting them as omens and messengers from the gods. We trace the gradual development of scientific understanding, from Aristotle's mistaken belief that comets were atmospheric phenomena to Edmund Halley's triumphant prediction of a comet's return. We travelled back in time to witness the birth of our solar system, watching as a vast cloud of gas and dust collapsed to form the Sun and its family of planets. We saw how asteroids formed in the warm inner regions of the solar nebula, rocky remnants of the planet-building process that were stirred up by Jupiter's gravity and prevented from assembling into a larger world. We learned how comets formed in the cold outer reaches, incorporating water ice and organic compounds that would be preserved for billions of years. We explored the asteroid belt, that river of ancient stone between Mars and Jupiter, home to millions of rocky bodies ranging from tiny pebbles to the dwarf planet Ceres. We discovered that the belt is not the crowded field of tumbling boulders depicted in science fiction, but rather a vast emptiness with occasional islands of rock separated by millions of kilometers. We learned about the different types of asteroids, from dark, carbon-rich C-types to bright, stony S-types to metallic M-types that may be the exposed cores of shattered protoplanets. We turned our attention to comets, those frozen wanderers from the edge of darkness, and marvelled at their transformation from inert chunks of ice into spectacular objects with glowing comas and tails stretching millions of kilometres. We learned about the structure of comet nuclei, their composition of ice and dust and organic compounds, and the processes that create the beautiful displays we observe when they approach the Sun. We ventured to the Kuiper Belt and the Oort Cloud, those vast reservoirs of icy bodies that supply the comets visiting the inner solar system. We contemplated the Oort Cloud's trillions of frozen objects orbiting in darkness at the very edge of the Sun's gravitational influence, occasionally nudged by passing stars into journeys that bring them close to the warmth of our star. We recalled famous comets that have graced human skies throughout history, from Halley's Comet with its appearances recorded across millennia, to the Great Comet of 1811, to the spectacular Hale-Bopp of 1997. We learned about notable asteroids, from Ceres and Vesta to the near-Earth objects that occasionally pass close to our planet and remind us of the dynamic environment in which we live. We explored the science of cosmic impacts, learning how collisions have shaped the history of our solar system and the evolution of life on Earth. We visited Meteor Crater in Arizona and contemplated the Chicxulub impact that ended the age of dinosaurs 66 million years ago. We considered the ongoing hazard posed by near-Earth objects and the efforts underway to detect and potentially deflect threatening asteroids. We celebrated the spacecraft missions that have carried human curiosity to these distant worlds. From Galileo's flybys of Gaspra and Ida to Rosetta's remarkable accompaniment of Comet 67P to the sample return triumphs of Hayabusa, and OSIRIS-REx. We look toward the future, considering the possibilities of asteroid mining, planetary defense, and continued exploration. Throughout this journey, we have seen that asteroids and comets are far more than mere debris or cosmic leftovers. They are time capsules from the dawn of our solar system, preserving information about conditions 4.6 billion years ago that has been erased on the larger planets. They are potential hazards that have shaped the course of life on Earth and could threaten our civilization in the future. They are resources that may one day support human expansion into space, and they are objects of profound beauty, gracing our skies with spectacular displays that have inspired wonder and contemplation throughout human history. The atoms in your body were once part of the solar nebula, perhaps incorporated into a planetesimal that was later shattered in a collision, its fragments eventually swept up by the growing Earth. In a very real sense, we are all made of asteroid and comet stuff, children of the same cosmic cloud that gave birth to these ancient wanderers. When we study asteroids and comets, we are studying our own origins. As you drift off to sleep, perhaps you will dream of frozen comets awakening as they approach the sun, their icy surfaces erupting with jets of gas and dust. Perhaps you will imagine the asteroid belt, that sparse archipelago of rocky worlds orbiting in eternal silence between Mars and Jupiter. Perhaps you will contemplate the Oort Cloud, that vast sphere of icy bodies at the edge of the Sun's domain, waiting in frozen darkness for the gravitational nudge that will send them falling toward the inner solar system. These ancient wanderers have been circling the Sun since long before humans existed, and they will continue their journeys long after we are gone. Yet in our brief moment of consciousness, we have reached out to touch them, sending our robotic emissaries across millions of kilometers to orbit them, land upon them, and bring pieces of them back to Earth. We have begun to understand their nature, their history, and their significance for our own existence. This understanding is one of humanity's greatest achievements, a testament to our curiosity, ingenuity, and determination to comprehend the universe in which we find ourselves. Thank you for joining me on this journey through the complete story of asteroids and comets. If you have enjoyed this exploration of our cosmic neighbourhood, please consider liking this video and subscribing to the channel for more journeys through the wonders of space. Your support helps us continue creating content that brings the marvels of the universe to curious minds everywhere.